Hello and welcome to Sleepy Science. Tonight, we are going to explore a possibility so strange that it almost breaks the mind. Somewhere, beyond everything we can see, there may be another version of you watching another version of this moment. A universe where one choice went differently. A universe with another Earth, another sky, another history, or laws of physics that would make life impossible to recognize. The multiverse is not just the idea of many worlds. It is the idea that reality may be far larger, deeper, and more unsettling than anything our senses were built to understand. But if infinite space can create infinite possibilities, then what does it really mean to be you? Before we begin, tell me in the comments where you are watching from, and if another version of you exists somewhere, what do you think they are doing right now? And if you enjoy calm science that makes reality feel stranger, don't forget to like the video. How infinite space could create infinite versions of you. The most unsettling version of the multiverse does not begin with portals, glowing doors, or another Earth floating beside ours like a secret twin. It begins with something much quieter and much harder to escape. Space may simply keep going, not just farther than your eyes can see, not just beyond the most distant galaxy, but onward, without an edge, without a final wall, without a last star where reality finally stops. You live inside the observable universe, a vast bubble of light around you, limited not by human weakness, but by the age of the cosmos and the speed at which light can travel. Beyond that horizon, there may be more space, more galaxies, more dust, more darkness, more chances for matter to arrange itself. And if space is truly infinite, then the strangest consequence is not that there may be aliens or unknown stars or distant versions of history. The strangest consequence is that somewhere, impossibly far away, there could be another arrangement of particles so similar to this one that it becomes another version of you. Not a mystical soul copy, not a fantasy clone. Just the same physical pattern repeated because an infinite stage gives even the rarest arrangement endless opportunities to appear. To understand why, start gently with a simple idea. The world around you is made from a limited set of ingredients arranged in enormously complex ways. Atoms combine into molecules, molecules into cells, cells into bodies, bodies into lives. The number of possible arrangements inside a region of space like our observable universe is unimaginably huge, far beyond anything your mind can comfortably hold. But huge is not the same as infinite. If the rules of physics allow only a certain range of particles, energies, and arrangements within a cosmic region, then an infinite universe creates a strange pressure on possibility. Give matter enough room, enough time, enough independent regions, and patterns do not merely happen once. They can happen again. A shuffled deck of cards feels random, but if you could shuffle forever, the same order would eventually return. The universe, if infinite, may be the deepest shuffle of all. Not cards in a hand, but galaxies, planets, weather systems, bodies, memories, and rooms like yours, arranged again and again across distances so large that reaching them is not just difficult, but physically hopeless. This does not mean science has proven another you exists. That part matters. We do not know whether space is infinite. We do not know whether the universe repeats in the exact way this idea suggests. And even if it does, such a copy would be separated from you by distances so enormous that no message could pass between you, no meeting could happen, no signal could confirm the resemblance. This is not a claim you can use like a fact in your hand. It is a possibility born from combining two ideas. Space may extend far beyond what we can observe, and physical arrangements may be finite within any one observable-sized region. From those ideas comes a haunting question. If reality has no edge, does uniqueness survive? You feel like a single, unrepeatable center of experience, and emotionally you are. No distant pattern, no mathematical repetition, no cosmic duplicate could steal the private warmth of your own awareness. But physically, the universe may not care about uniqueness the way you do. It may be less like a museum, where every object is one of a kind, and more like an endless ocean, where waves eventually form similar shapes, because the same laws keep moving through the same possibilities. Somewhere beyond the cosmic horizon, there might be a planet where the continents almost match Earth, where a person with your face once looked up at a sky almost like this one, where a life unfolded with tiny differences you would never know. Farther still, if the idea is pushed to its extreme, there might be a region where every detail matches. The same room, the same breath, the same thought arriving at this exact moment. But notice how carefully this must be held. It is not that the universe is trying to copy you. It is not that there is a cosmic plan producing duplicates. It is simply that infinity changes probability. In a small room, rare things may never happen. In an endless room, the word rare begins to lose its power. And this is where the idea becomes more than astronomy. It reaches inward. Because if another version of you could exist somewhere beyond all possible contact, what does it mean to be you? Are you the pattern of your atoms, the continuity of your memories, the awareness reading this moment from the inside? If a perfect physical duplicate existed, with the same memories and the same personality, would that person be you, or only someone who believes they are you with absolute sincerity? The science gives us the stage, but the question becomes philosophical. Identity may not be a single object, but a fragile stream, held together by memory, body, and perspective. A copy could share your structure, but not your viewpoint. It could contain your history, but not your exact center of experience. It would wake up as itself, not as a remote extension of you. And that may be the most important comfort inside the strangeness. Infinite space might make your pattern repeatable, but it does not make your living moment replaceable. The breath you are taking now is still yours. The choices you make inside this small circle of light still matter here, where you can feel them. The unreachable vastness beyond the horizon does not make your life smaller. It makes it more mysterious. It tells you that existence may be far larger than the part that has touched your eyes, and that reality may contain possibilities too distant to ever become evidence, yet too logical to dismiss completely. So when you look into the night sky, you are not just looking at stars. You are looking toward a boundary made by light, time, and ignorance. Beyond it may be emptiness, or more galaxies, or an endless repetition of cosmic patterns. Perhaps no other you exists, perhaps countless versions do, but either way, the lesson is the same. You are living inside a universe whose true size may be beyond measurement, beyond travel, beyond imagination. And in that vastness, your awareness is not less meaningful. It is more delicate, more unlikely, more luminous. A brief island of knowing inside a space that may never end. The strange idea of parallel Earths. Somewhere in the human mind, there is a door that never fully closes. The thought that Earth may not be the only Earth-like story reality knows how to tell. Not a magical mirror world hanging a few steps away in the darkness. Not a secret planet where your life is being replayed for dramatic effect. But a stranger and more serious possibility that under the right conditions, nature may build worlds that rhyme with ours. A parallel Earth, in the honest scientific sense, is not something we have discovered. No telescope has looked across space and found another blue planet with the same oceans, the same cities, the same history, the same familiar faces moving beneath different clouds. But the idea survives because Earth itself is not made from supernatural ingredients. It is rock, metal, water, atmosphere, sunlight, chemistry, gravity, time, and a long chain of accidents that somehow became biology. And if those ingredients exist elsewhere, if planets form around other stars by the same physical laws, then the question becomes unavoidable. How many times can the universe make something that feels, from a distance, like home? This is where the idea becomes fascinating without becoming false. We already know that planets are not rare decorations. Stars commonly form with disks of gas and dust around them, and from those disks, worlds are born. Some are giant and violent, wrapped in crushing atmospheres. Some are frozen stones. Some are scorched deserts. Some may sit in a gentler region around their star, where liquid water could exist on the surface. But an Earth-sized planet in a comfortable orbit is only the first page of a much longer book. To become truly Earth-like, a world may need a stable climate, a protective atmosphere, the right chemical cycles, enough geological activity to recycle carbon, perhaps a magnetic field, perhaps a large moon to help steady its rotation, perhaps long stretches of calm between catastrophes, and also enough catastrophe to reshape life without ending it completely. Earth is not just a location. Earth is a balance. Too much heat and oceans vanish. Too little and they freeze. Too much atmosphere and the surface suffocates beneath pressure. Too little and the planet becomes exposed and sterile. Life here did not appear inside a perfect paradise. It emerged inside a restless machine, a planet constantly trading energy between stone, ocean, air, and sunlight. So when people say parallel Earth, they often picture another version of our world. But science asks a more careful question. Could there be planets that follow a similar recipe while producing very different outcomes? One such world might have oceans deeper than ours, with no continents rising above the waves. Another might have redder skies because its star shines differently. Another might have life, but not forests, not animals, not intelligence, only quiet microbial layers changing the chemistry of the air for billions of years. Another might have been almost Earth, but lost the fragile race early. Its water boiled away, its atmosphere thinned, its core cooled, or its climate tipped beyond recovery. The strange idea of parallel Earths teaches you that Earth-like is not one thing. It is a spectrum from worlds that only match our size, to worlds that might share our chemistry, to worlds that could carry living systems, to the far more speculative dream of a planet that mirrors our history in recognizable ways. And the deeper you go, the more the idea becomes less about copies and more about contingency. Change one event in Earth's past, and the world you know may never appear. No asteroid impact at the wrong time, and mammals might remain small shadows beneath ancient reptiles. A slightly different atmosphere, and fire might behave differently. A different arrangement of continents, and ocean currents could alter climate, migration, and evolution. Even the rise of intelligence was not guaranteed. It was not written into the rocks from the beginning. It was a fragile result of countless pressures, extinctions, mutations, and opportunities. This means another Earth-like planet could be physically similar to ours and still never produce anything like us. It could be alive but silent, beautiful but mindless, green but without eyes to admire the green. Or it could produce awareness in a form so unfamiliar that calling it human would be a failure of imagination. That is the real power of the parallel Earth idea. It does not simply ask whether there is another home out there. It asks what makes a home become conscious of itself. When astronomers search for distant planets, they are not looking for science fiction scenery. They are looking for clues in starlight, tiny dimmings when a planet crosses its star, subtle wobbles caused by gravity, hints of atmospheric gases that may one day suggest oceans, clouds, or biological activity. These methods are delicate, indirect, and limited. A planet can whisper its presence across light years, but it does not easily reveal its story. We may know its size before we know its sky. We may know its orbit before we know whether rain ever touches its surface. And even if we find a world with oxygen, water vapor, and a friendly temperature, we will still have to be careful. Nature can imitate signs. Chemistry can mislead. A possible biosignature is not a forest. A habitable world is not automatically inhabited. Science moves slowly here because the question is too important for shortcuts. Yet the emotional pull remains. A parallel Earth would change something in us, even if no one lived there. It would tell us that our planet is not a cosmic accident so rare that reality only tried once. It would place Earth inside a wider family of worlds, each one an experiment in balance, each one a different answer to the same physical question. What can matter become when given time, warmth, and complexity? And if one day we found a truly living Earth-like planet, the discovery would be both humbling and intimate. Humbling, because it would show that life is not a private miracle reserved for this small blue sphere. Intimate, because it would make the universe feel less empty without making it less mysterious. Still, the conclusion must stay honest. Parallel Earths remain an idea, not a confirmed reality. We have found many worlds beyond the Sun, and some may share certain Earth-like traits, but we have not found another Earth in the full sense. No second cradle, no confirmed living twin, no distant mirror with oceans breathing under familiar clouds. What we have is something quieter, evidence that planet-making is common, that Earth-like conditions are worth searching for, and that the universe has enough variety to keep the question alive. So the next time you hear the phrase parallel Earth, do not picture only a duplicate of your street, your room, your reflection. Picture instead a vast cosmic laboratory where planets turn in the dark around other suns, where some are failed Earths, some are almost Earths, some may be living Earths of a kind we have no language for yet. And then return gently to this one, because until another is found, Earth is not just our planet. It is our only known example of matter waking up, looking back at the sky, and wondering whether somewhere, under another sun, another world has begun to wonder too. Quantum mechanics and the many worlds interpretation. A quantum particle does not enter reality the way a stone enters a room. It arrives more like a question that has not yet chosen its answer. At the scale of ordinary life, the world feels definite. A cup is on the table or it is not. A door is open or closed. A person is here or somewhere else. Your senses are trained by a universe that seems to make decisions before you arrive. But when physics looks beneath the surface of matter, that confidence begins to loosen. Tiny systems such as electrons, photons, and atoms do not always behave like little solid objects with clear positions and fixed paths. Before measurement, quantum theory describes them as existing in a spread of possible outcomes, not because scientists are simply confused, but because the theory itself treats possibility as part of the physical description. This is where the mystery begins. When a measurement happens, we only see one result. The detector clicks in one place. The atom is found in one state. The photon leaves one mark. But the mathematics of quantum mechanics seems to carry all the possible outcomes forward with a strange and elegant precision. So the question is not whether quantum mechanics works. It works with astonishing accuracy. The deeper question is what it means. Does reality truly collapse into one result when measured? Does the act of observation somehow force nature to choose? Or is something even stranger happening beneath the calm surface of the experiment? The many worlds interpretation offers one of the most haunting answers. Maybe the other outcomes do not vanish at all. Maybe they continue, but no longer inside the same branch of reality you experience. In this view, the universe does not collapse. It splits in a subtle, physical sense. Not like glass breaking dramatically. Not like a doorway opening beside you, but like a vast wave separating into streams that can no longer meet. Each possible result becomes real in its own branch, while you only find yourself inside one of them. This idea was proposed by Hugh Everett in the 20th century as a way to take the equations of quantum mechanics seriously without adding a special rule that says the wave suddenly collapses when someone measures it. Instead of asking why possibility disappears, Many World says, perhaps it never disappears. Perhaps reality is larger than the single outcome you are allowed to remember. To understand this carefully, do not picture cartoon universes popping into existence every time you decide what to eat. That is too simple and often misleading. The branching in many worlds is tied to quantum events becoming entangled with measuring devices, environments, and eventually observers. When a tiny system interacts with the wider world, its alternatives spread outward into the environment so thoroughly that they stop interfering with one another. This process is called decoherence, and it is one reason the world around you appears stable instead of ghostly and blurred. The alternatives still exist in the theory, but they become effectively separated, like radio stations broadcasting at once while your receiver is locked to only one frequency. You do not feel the other branches. You do not receive memories from them. You cannot send a message to the version of the experiment where a different result occurred. From inside your branch, the world feels singular because every record around you agrees with the same outcome. The notebook, the machine, your eyes, your memory, the air molecules touched by the event. This is why many worlds is not a fantasy of easy travel between timelines. It is not a promise that another you can be reached. It is an interpretation of why quantum measurements give definite experiences, while the underlying theory may remain smooth, continuous, and full of alternatives. And this is also why scientists disagree about it. Many worlds is respected by some physicists because it removes the mysterious collapse and lets the quantum wave evolve according to one rule. Others are cautious because interpretations can produce the same experimental predictions, making them hard to confirm directly. The debate is not between science and imagination. It is between different ways of understanding a theory that already works. One view says nature selects one result. Another says all results occur, but observers become part of only one version. Both are attempts to answer the measurement problem, the uncomfortable gap between quantum possibility and the single world we actually see. And now the idea turns inward. If many worlds is true, your sense of reality is not wrong, but it is incomplete. You are not standing at the center of all existence. You are traveling along one thread of a much larger fabric. Every measurement that touched the world before you were born, every quantum event inside stars, rocks, machines, and living cells may have helped separate reality into countless non-communicating histories. Not because the universe is trying to tell a story, but because the rules of matter may be richer than human experience can hold. This can feel overwhelming at first, almost cold. If every outcome exists somewhere, does this life lose meaning? Does this version of you become less important? Strangely, the answer may be no. Meaning does not come from being the only branch. It comes from being the branch you inhabit. Pain still hurts here. Kindness still matters here. A promise kept in this world is not weakened by the possibility that another branch contains failure. Your life is not a vote among infinite copies. It is the only stream of awareness available to you. Many worlds, if true, does not make your choices meaningless. It makes your experience local, fragile, and deeply specific. You are not watching the full wave of reality from the outside. You are inside one unfolding strand with memory behind you and uncertainty ahead. And perhaps that is what quantum mechanics has been quietly teaching all along. The universe may not be built to satisfy the human desire for one clean, final picture. It may be layered, branching, and stranger than certainty can tolerate. So when you hear that a particle can exist in multiple possible states, do not treat it as a magic trick. Treat it as a warning from the foundations of matter. The world you see may be only the visible face of a deeper structure, one where possibility is not merely imagined before reality begins, but woven into reality itself. And somewhere beyond your reach, not across space, but across the hidden architecture of quantum history, other outcomes may continue silently. You will never shake their hands. You will never hear their voices, but the thought of them changes the room you're sitting in. It reminds you that certainty is a narrow light, and existence may be the darkness around it, wider than anything you can see, yet close enough to shape every moment you call real. Every choice, every outcome, every branch. A single choice can feel small enough to disappear, yet from inside your life it can divide everything into before and after. You turn left instead of right. You answer the message or leave it unread. You speak honestly, stay silent, board the train, close the door, forgive, refuse, begin again. Human beings naturally imagine these moments as forks in a road, as if every decision leaves behind a ghost road you did not take. And this is why the phrase, every choice, every outcome, every branch, feels so powerful. It seems to join your private life to one of the strangest ideas in physics. But here is the truth that makes it more interesting, not less. The many worlds idea does not simply say that every human choice magically creates a new universe. That version is dramatic but too simple. In physics, branching is not centered on your personal decisions. It begins with quantum systems, with tiny events whose possible outcomes become entangled with the world around them. Most of these branchings have nothing to do with human drama. They happen in detectors, in atoms, in light, in dust, in distant stars, in countless interactions too small and too fast for any mind to notice. Reality, if this interpretation is right, is not splitting because you are choosing tea instead of coffee. Rather, your choice is carried by a physical world already full of branching processes beneath the surface. The decision you experience as one clear moment may be built from layers of brain activity, memory, chemistry, emotion, and environment, all resting on matter that obeys quantum rules at its deepest levels. This does not mean your choice is fake. It means your choice is not floating above nature like something separate from the universe. It is nature becoming personal. In ordinary life, the roads not taken fade into imagination. You can wonder about them, regret them, romanticize them, but you cannot visit them. In a many worlds picture, some alternative outcomes may not simply disappear from the full physical description. They may continue as separate branches that no longer communicate with yours. But this should be held carefully. It is not a proven fact that all your missed opportunities are living somewhere like scenes in a hidden film. It is an interpretation of quantum mechanics, one serious way of understanding why only one outcome appears in your experience, while the theory itself may preserve many possibilities. The key lesson is not everything you can imagine exists. The key lesson is subtler. The world may contain more outcomes than any single observer can experience. Your consciousness is narrow, not because it is weak, but because experience is always local. You live along one branch, with one chain of memories, one body, one history behind your eyes. If another outcome exists elsewhere in the larger structure, it is not a spare life you can borrow. It does not soften the consequences here. A cruel word spoken in this branch still wounds someone in this branch. A chance avoided here is still avoided here. A kindness offered here still changes the only world you can touch. This is where the idea becomes morally sharper than it first appears. Some people hear every outcome happens and think it makes choice meaningless, as if responsibility dissolves because somewhere another version did the opposite. But that is not how lived reality works. Meaning is not distributed across branches and averaged out. Meaning happens where awareness, memory, and consequence meet. You are accountable to the branch you inhabit because it is the only one available to your hands. If you help someone here, the warmth is real here. If you waste your life waiting for another version of you to be brave, nothing in this room becomes braver. Many worlds, when understood honestly, does not excuse you from choosing. It makes choosing feel more intimate, because every decision is the point where vast physical possibility becomes a single remembered life. And even outside quantum theory, this is already how the mind works. You are haunted by possible selves. The person you might have become if you had stayed, left, tried sooner, trusted less, studied more, apologized earlier. These selves are not necessarily real in a physical sense, but psychologically they shape you. They are inner branches, not cosmic ones, and they can be powerful. A person can suffer more from an imagined life than from the life actually lived. Regret is the mind standing at a closed junction, staring down a road it can no longer enter. Hope is the opposite, a branch not yet chosen, still trembling with possibility. And perhaps this is why the physics feels so personal. It gives a scientific shadow to something you already know emotionally. Life is not experienced as a straight line, but as a narrowing field. At every moment, the future begins wide and then becomes specific. The menu collapses into the meal. The sentence collapses into the words you actually say. The years collapse into the face you eventually recognize as your own. Yet this narrowing is not only loss, it is also creation. A life with every possibility still open would not be a life. It would be a fog. To become someone, you must let most possibilities pass away. You must choose shape over infinity. You must become real in one direction. So the thought of endless branches should not only frighten you, it should also return you to the quiet power of this moment. You do not need to know whether the entire cosmos contains every outcome in order to understand that your attention is limited, your time is limited, your tenderness is limited, and therefore precious. The branch you are in may be one thread among many, or it may be the only world that ever becomes real. Science has not settled that question. But either way, this is the thread you can feel. This is the room where your breath is happening. This is the life where your next choice arrives. Not as a symbol, not as a theory, but as a small pressure in the chest, asking what kind of future you are willing to make actual. And maybe that is the deepest lesson hidden inside the language of branches. Not that somewhere everything happens, but that here, something happens because you answer. What the multiverse does to the meaning of reality. Reality begins to feel different the moment you stop treating the universe as the final container of everything that exists. For most of human history, reality meant one world, one sky, one Earth, one cosmic story unfolding around us. Even when we learned that Earth was not the center, even when the sun became one star among many, even when galaxies turned out to be islands in a far larger darkness, the basic feeling remained the same. There is one total stage, and we are somewhere inside it. But the multiverse changes that feeling at its root. It does not simply add more places to the map. It questions what a map is. It asks whether our universe is the whole of reality, or only one region, one expression, one possible outcome within something larger. And once that question enters the mind, reality stops feeling like a single finished object and begins to feel more like a hierarchy. What you see, what instruments can detect, what theory can infer, and what may exist forever beyond direct contact. This is why the multiverse is not just a scientific speculation about distant domains. It is a pressure applied to the meaning of the word real. In ordinary life, real means accessible. A chair is real because you can sit on it. A star is real because its light reaches your telescope. A memory is real in a different way, because it shapes your behavior even if no one else can touch it. But what about a universe that can never send us light, never exchange a signal, never leave a mark in our detectors? If it is predicted by a serious theory, if it follows from equations that explain things we can observe, is it real in the same sense as this room? Or is it only a useful idea, a shadow cast by mathematics? The multiverse forces science and philosophy to stand very close together, because the usual boundary between evidence and meaning becomes thin. Scientists do not accept an idea just because it feels profound. A multiverse must earn its place by helping explain something. Why our universe has the properties it has, why the laws seem tuned in a certain way, why inflation might naturally produce many cosmic regions, why quantum theory may describe more than one outcome. But even then, there is a difference between a theory that is useful and a reality that is confirmed. This distinction matters. The multiverse should not be sold as a proven landscape of endless worlds. It is not a photographed place. It is not a destination. It is a set of possibilities that arises from several serious lines of thought, each with its own strengths and uncertainties. And yet, even as a possibility, it changes the emotional architecture of reality. If our universe is one among many, then the old human instinct to see our world as the central fact of existence begins to weaken. The laws we call fundamental may be local conditions. The constants we treat as deep necessities may be environmental features. What feels inevitable from inside our universe might be only one allowed arrangement within a wider structure. This does not make our universe fake. It makes it situated. A fish living in one lake may believe water has only one temperature, one color, one chemistry, until it learns there are other lakes beyond the hills. The fish's lake does not become unreal. It becomes contextual. That is what the multiverse does to reality. It turns absolutes into local truths. It makes you ask whether the deep features of existence are universal laws or regional habits. It also changes how we think about explanation. In a single universe picture, if a number in physics appears strangely perfect for stars, chemistry, or life, we search for a reason why it had to be that way. In a multiverse picture, another kind of explanation becomes possible. Perhaps many different cosmic regions have different conditions, and we naturally find ourselves in one compatible with observers. This is powerful, but also dangerous if used carelessly. It can explain why our universe permits life, but it can also tempt people to stop asking deeper questions. A good explanation should illuminate, not numb curiosity. The multiverse is meaningful only if it sharpens the search, not if it becomes a place to hide every mystery. And then there is the personal shock. If reality is larger than our universe, what happens to significance? Some people feel diminished by the thought. If there are countless cosmic domains, if existence is vast beyond contact, does one human life become almost nothing? But scale has always tried to intimidate meaning. The ocean does not make a single drop imaginary. A library does not make one sentence worthless. Meaning is not measured by how much space something occupies. It is measured by relation, awareness, consequence, and depth of experience. Even if our universe were one among many, your pain would still matter to the person who loves you. Your choices would still change the future available here. A child learning the name of a star would still be a real event inside consciousness. The multiverse may reduce cosmic centrality, but it does not erase lived value. In fact, it may make reality more delicate. If this universe is only one possible way existence can unfold, then the exact texture of this world becomes more precious, not less. The way light scatters in our atmosphere, the chemistry that makes breath possible, the narrow conditions that allow memory, language, grief, music, and wonder. Reality becomes not a single command, but a rare arrangement you happen to be inside. And perhaps the deepest change is this: the multiverse teaches humility without demanding despair. It says that what you call everything may not be everything. It says that the visible is not always the complete. It says that truth may come in layers, and that the human mind may be built to live inside one layer while longing for the others. We may never know whether the multiverse is physically real in the strongest sense. Future theories may support it, reshape it, or replace it. But the question it leaves behind is already real inside us. Can we accept that reality may be larger than proof, while still respecting proof as our only honest guide? That tension is where mature wonder lives. Not in believing every possibility, and not in dismissing every mystery, but in standing carefully between them. So the multiverse does not destroy the meaning of reality. It makes reality less like a wall and more like a depth, less like a finished answer and more like a horizon that moves as understanding grows. And you, listening from one small point within one known universe, are not outside that mystery. You are one of the ways it becomes aware of itself, one of the brief places where reality pauses, opens its eyes, and asks what else it might be. Can we ever travel to another universe? The dream of reaching another universe sounds like escape, but the first truth is colder. We do not even know whether there is a road. When people imagine traveling beyond our universe, they picture a boundary somewhere far away, a cosmic shoreline where one reality ends and another begins, as if a ship could cross the dark and arrive under a different set of stars. But physics does not give us that kind of border. A universe, in the deepest sense, may mean everything connected by the same space, time, and physical laws. Another universe may not be a distant island inside the same ocean. It may be a separate ocean altogether, with no shared water between them. And that changes the question completely. Traveling to another universe is not like traveling to another galaxy, where the problem is enormous distance, but the rules remain familiar. It is more like asking whether a character printed on one page can step into a different book without tearing the paper of both. The first obstacle is not engineering. It is definition. What kind of other universe do you mean? If it means a region beyond what light from our cosmos can ever show us, then it may still be part of the same larger space, but unreachable, because the expansion of the universe and the speed of light limit what can ever affect us. If it means a separate bubble universe born from cosmic inflation, then it may be causally sealed away, not merely far, but disconnected in a way no rocket can overcome. If it means a quantum branch, then it is not sitting in a direction you can point toward. It is separated by the structure of measurement and decoherence, not by miles. If it means a higher dimensional brain or a different layer of reality, then travel would require physics we do not currently possess and may never possess. So the honest answer begins here. With current science, there is no known method to travel to another universe. No confirmed portal, no tested doorway, no machine hiding in theory, waiting only for better metal. This does not make the question foolish. It makes it profound, because the question teaches you how strict reality is about connection. In our universe, even reaching nearby stars is almost unbearably difficult, Light itself takes years to cross the space between suns, thousands of years across parts of our galaxy, millions of years to neighboring galaxies, and far longer across the deepest visible cosmos. A spacecraft cannot simply ignore this. The speed of light is not only a speed limit for objects, it is a limit on cause and effect, on how quickly one part of the universe can speak to another. If another universe lies beyond causal contact, then it is not just hidden. It is outside the conversation. It cannot receive our signal. It cannot answer. It may exist in theory and remain forever silent in practice. That is the quiet brutality of cosmic separation. Not that something is far, but that distance becomes a kind of erasure. Of course, human imagination searches for loopholes. Wormholes appear in the mind almost instantly. Tunnels through space-time, shortcuts that might connect distant regions without forcing a traveler to cross the space between. In general relativity, certain mathematical solutions do resemble bridges, and this is why wormholes are not pure fantasy. But a mathematical possibility is not a usable tunnel. A traversable wormhole, if it could exist, would likely require forms of matter or energy with properties we have never learned to gather, stabilize, or shape. It would need to stay open instead of collapsing. It would need not to destroy the traveler. And even then, a wormhole would not automatically connect to another universe. It might connect two regions of this one, or it might be impossible to use at all. The same caution applies to warp drives. Some equations suggest that space-time could, in principle, be compressed in front of a ship and expanded behind it, allowing effective faster-than-light travel without locally breaking the light speed rule. But these ideas remain speculative and appear to demand exotic conditions far beyond anything known. They are not blueprints, they are stress tests for the imagination of physics. Black holes are another tempting myth. Because they bend space and time so violently, people wonder whether falling into one could lead somewhere else. But the known reality is not kind. A black hole is not a doorway in the everyday sense. For a traveler crossing the event horizon, return becomes impossible. Tidal forces may become fatal, and whatever lies deeper is hidden behind a boundary our current theories struggle to fully describe. Some speculative models discuss baby universes or cosmic bounces, but these are not travel plans. They are attempts to understand the edge of known theory. You cannot steer through a singularity like a tunnel under a mountain. You cannot book passage through a place where prediction itself breaks down. And yet, the impossibility is not the end of wonder. It is the beginning of a more mature kind of wonder, because asking whether we can travel to another universe reveals that travel may be too human a word for the scale of the question. Travel assumes a path, a vehicle, a before and after, a traveler who remains themselves from departure to arrival. But another universe may not share the same time. It may not have a compatible direction of causality. It may not allow matter like ours to exist. Even if there were a bridge, what would cross it? Your body depends on the laws of this universe. The strength of atoms, the behavior of light, the chemistry of water, the stability of particles. A universe with different physical laws might not be a place you could visit. It might be an environment where the very structure of you has no meaning. This is the part science fiction often softens. It imagines other universes as decorated versions of home. But physics allows a harsher possibility. Some realities, if they exist, may be so different that arrival would be indistinguishable from destruction. So perhaps the real answer is this. We may never travel to another universe physically, but the question still expands us. It forces us to separate hope from evidence, possibility from promise, equations from engines. It teaches that the universe is not obligated to provide exits just because the human mind dislikes walls. And still, there is something beautiful in the reach. A creature made of local atoms, born on a small planet, surrounded by one sky, is capable of asking whether existence has hidden rooms beyond all contact. That question itself is a kind of journey, not through a portal, but through understanding. For now, another universe, if it exists, is not a destination. It is a limit drawn around our knowledge, a dark coastline we can think toward, but not cross. And maybe that is enough for tonight. Not the fantasy of escape, but the humility of realizing that some doors may never open, and yet the act of standing before them can still change the way you see the room you're already in. The simulation hypothesis and artificial universes. The most dangerous version of the simulation hypothesis is not the childish idea that your world is fake, but the quieter possibility that reality and computation may be closer than human comfort wants them to be. You do not need to picture a glowing screen beyond the sky, or a careless programmer watching your life like a game. That image is dramatic, but it can make the real idea smaller than it is. The serious question is not simply, are we inside a computer? The serious question is whether a universe could be artificially generated with enough depth, consistency, and internal law that the beings inside it would experience it as reality. We already create tiny artificial worlds. Not conscious worlds, not living universes, but simplified spaces where rules unfold. Weather models, galaxy simulations, virtual ecosystems, artificial intelligence environments, physics engines where digital objects fall, collide, evolve, and respond. These are not illusions to the systems inside them, because the systems inside them have no inner experience that we know of. But they show something important. A world can be made from rules rather than from stone. A simulated galaxy is not a real galaxy, but its spiral structure can still teach us something about gravity. A virtual organism is not alive in the biological sense, but its behavior can still reveal how complexity grows from simple instructions. From here, the simulation hypothesis takes a slow and unsettling step forward. If intelligence keeps advancing, could future civilizations build artificial universes rich enough to contain observers? And if such observers existed, would they have any way to know the difference from the inside? This is where honesty matters. There is no confirmed evidence that we live in a simulation. No glitch in the sky has been verified. No experiment has proven a hidden computer beneath physics. The hypothesis remains philosophical and speculative, tied to questions about technology, consciousness, computation, and what it means for something to be real. One famous argument suggests that at least one of three things may be true. Advanced civilizations never reach the power to run ancestor-like simulations, or they choose not to run them, or simulated observers could eventually become far more common than biological ones. But this is not a scientific verdict. It is a reasoning structure, a way of forcing the mind to confront consequences. Its strength is not that it proves you are simulated. Its strength is that it makes your definition of reality less lazy. Because if a simulated mind could feel pain, remember childhood, fear death, love someone, and ask whether its world is real, would the word artificial make its experience meaningless? A candle painted in a picture gives no heat. But a mind inside an artificial universe, if conscious, would not be a painting. It would be an event happening from the inside. Its fear would not be fake to it. Its wonder would not be fake to it. This is the uncomfortable line the simulation hypothesis draws. The material underneath experience may matter less to consciousness than the structure that supports it. Your brain already turns electrical activity into color, sound, memory, and selfhood. You never touch the outside world directly. You live through a controlled internal model built by biology. A simulated being, if such a being were possible, might live through a controlled internal model built by computation. The difference could be enormous from the outside, but strangely invisible from within. Artificial universes also raise a second question. Why would anyone make them? Not necessarily for entertainment. A civilization might simulate universes to study history, test physics, explore possible futures, understand consciousness, or preserve extinct worlds. A simulated cosmos could be a laboratory, an archive, a classroom, or a failed experiment left running long after its creators forgot the question. But again, these are possibilities, not facts. The danger is to let the idea become a lazy explanation for everything mysterious. If something strange happens, that does not mean reality has glitched. If physics has limits, that does not automatically mean those limits are computer code. Real science must separate metaphor from evidence. The universe may be mathematically describable, because mathematics is the language we use to describe patterns, not because the stars are pixels. Quantum uncertainty does not automatically mean a rendering engine. The speed of light does not automatically mean processor lag. These comparisons are interesting, but they are not proof. And yet, even without proof, the hypothesis performs a deeper service. It makes you ask what kind of reality would be enough. If tomorrow you learned with certainty that your universe was artificial, would gravity stop pulling you? Would love stop hurting? Would music stop moving through your chest? Would guilt become harmless? Or kindness unnecessary? Probably not. The revelation would change the frame, but not the lived weight of being conscious. A dream ends when you wake up. But if a simulated life never wakes into anything else, then for the one living it, it is still the only horizon available. This is why the simulation hypothesis can be frightening at first, and then strangely grounding. It threatens the old comfort that reality must be natural to be meaningful, but it also reveals that meaning was never guaranteed by the material of the universe. Meaning comes from relation, awareness, memory, consequence, and care. If this world is fundamental, those things matter. If this world is artificial, they still matter inside it. The question is not only whether the cosmos was built. The question is whether built things can become sacred once they begin to feel. And perhaps that is the softest, strangest ending the simulation hypothesis offers. Even if reality were an artificial universe, even if the deepest flaw beneath matter were information rather than stone, your life would not become empty. It would become more mysterious. You would still have to choose gently, speak truthfully, and live as though the pain and beauty around you are real enough to deserve reverence. Because whatever the universe is made of, you are experiencing it from within. And from within, experience is never nothing. Why other universes might have different laws of physics. A universe with different laws would not look like a stranger version of our home. It might not look like anything your mind can turn into a picture at all. When people imagine another universe, they often repaint this one with new colors. Different stars, different planets, different creatures. Maybe a sky with unfamiliar constellations. But the deeper possibility is far more radical. Another universe, if it exists, might not simply contain different objects. It might run on different rules. Its matter might not bind the way ours does. Its light might behave differently. Its atoms, if it has atoms at all, might not form stable structures. Gravity might be stronger, weaker, or shaped in ways that never allow galaxies to gather. Chemistry might fail before it begins. Time might not permit the kind of ordered change that memory depends on. And this is where the idea becomes both scientific and deeply unsettling. The laws of physics we experience may feel eternal, because they are all we have ever known, but feeling inevitable is not the same as being inevitable. In our universe, reality depends on a delicate cooperation between forces and constants. Gravity pulls matter together so stars and galaxies can form. Electromagnetism allows atoms and molecules to exist. Nuclear forces hold atomic nuclei together and power stars. The masses of particles, the strength of interactions, the behavior of space, the balance between expansion and structure, all of these features create the stage on which complexity becomes possible. Change them too much, and the universe may still exist, but it may be sterile, brief, chaotic, or empty of anything that could ever wake up and ask why. This does not mean scientists know that other universes with other laws are real. They do not. We have no confirmed observation of a separate universe with different physics. What we have are theories that open the door to that possibility. In some areas of modern physics, what we call the laws may partly depend on the state of the vacuum. And the vacuum is not simply empty space. It is the lowest energy condition of fields, the background setting that determines how particles behave. If a deeper theory allows more than one possible vacuum state, then different regions of reality could settle into different physical conditions, almost like water freezing into different crystal patterns under different circumstances. The underlying framework might be shared, but the local rules could differ. This is a strange idea because it turns physics from a single commandment into something more like a landscape of allowed possibilities. Our universe may be one valley in that landscape, stable enough for stars, rich enough for chemistry, slow enough for evolution, and balanced enough for consciousness to emerge. Another valley could produce a cosmos where matter collapses too quickly. Another could produce particles that never combine into atoms. Another could expand so violently that structure never forms. Another might last only a flicker before dissolving into radiation. From the inside, each universe would treat its own rules as normal. There would be no outside comparison, no cosmic laboratory wall listing the alternatives. Any observers that did arise would naturally find themselves in a universe compatible with their existence. Not because the universe cared about them, but because incompatible universes would have no one inside them to wonder. This idea is important because it changes the way we think about necessity. When you drop a stone, gravity feels like a final truth. When light travels, when atoms bond, when the sun burns, the rules feel absolute. But perhaps some features of physics are more like environmental facts than ultimate facts. The laws here may be the climate of our cosmic region, not the entire weather of existence. That does not make them weak or unreal. A local law can still be completely binding for everything inside it. You cannot negotiate with gravity just because another universe might have a different version of it. You cannot step outside the constants that built your body. Your bones, your breath, your memories, even the electricity moving through your nervous system, all depend on the particular physics of this universe. If those rules were slightly different, you might not merely be different, you might be impossible. This is why the thought of different physical laws is not just abstract science. It presses directly on the mystery of why anything like us can exist at all. We are not floating above physics, using it from a distance. We are physics arranged into awareness. The same rules that shape stars also shape the chemistry in your cells. The same balance that allows atoms to exist allows thoughts to form, language to carry meaning, and eyes to look back at the night sky. So when you ask why other universes might have different laws, you are also asking why this universe has laws gentle enough to hold you together. And the honest answer is still unfinished. Maybe there is one deep law that forces everything to be exactly as it is, and we have not discovered it yet. Maybe there are many possible sets of laws, and we live in one that happens to permit complexity. Maybe the question itself will change as physics grows deeper, but the possibility remains haunting. Reality may not be a single rulebook printed once for all existence. It may be a library of rulebooks, most of them unreadable to minds like ours, most of them incapable of producing minds at all. And here, in this one readable volume, matter learned to burn as stars, cool into planets, gather into oceans, and eventually become you, listening in the dark, realizing that the laws you take for granted may be the most intimate inheritance you have ever received. Bubble universes floating beyond our reach. A bubble universe would not float through space like a soap bubble in the air, because the space around it is part of the mystery itself. The image is beautiful, but it can mislead you if you hold it too literally. These bubbles are not objects drifting inside our night sky, not glowing spheres beyond the farthest galaxies, not places you could reach if only your spacecraft were fast enough. In the language of cosmology, a bubble universe is a possible region where cosmic inflation has ended locally, allowing space to cool, particles to form, and a universe like ours to begin its slower history. Around it, in some versions of the theory, inflation may continue elsewhere, stretching the background so violently that other regions become forever unreachable. So the bubble is not floating in space the way a planet floats around a star. It is more like a calm pocket forming inside a storm that never fully stops. Inside the pocket, structure can appear. Radiation, matter, gravity, galaxies, perhaps planets, perhaps observers. Outside, the inflating background keeps expanding so quickly that other pockets are carried away from one another before any message can pass between them. This is why bubble universes are described as beyond our reach, not because they are merely distant, but because the geometry of space-time may prevent contact altogether. If our observable universe is inside one such bubble, then the boundary is not a wall you can fly toward. It is woven into the way our region began, cooled, and became causally connected to itself. To understand why scientists even consider this, you have to return to the early universe, when inflation was proposed to explain several strange features of the cosmos. Why the universe looks so smooth on large scales, why distant regions have similar temperatures, and why space appears so close to flat. Inflation says that a tiny region of the early cosmos expanded at an extraordinary rate, stretching small quantum irregularities into the seeds of later cosmic structure. But in some models, inflation does not end everywhere at once. It ends in one region, then another, each ending like a local release of trapped energy. When inflation ends inside a region, that region can become a bubble universe. When it continues outside, more bubbles may form later. The result is not one explosion into emptiness, but a larger process of cosmic budding. Pockets of ordinary expansion appearing within a wider inflating background. This remains speculative. It is not a confirmed map of reality. No telescope has photographed another bubble universe. No signal has arrived from one. The idea belongs to the frontier where strong theory meets limited evidence, and that boundary must be respected. But even as a possibility, it teaches something real about the nature of scientific imagination. Scientists do not imagine bubble universes simply because they sound dramatic. They appear as a consequence of trying to understand inflation deeply. If the mechanism that drove inflation can continue in some places while ending in others, then our universe may not be the whole event. It may be one cooled region among many, and each bubble, once formed, could become internally enormous. From inside, its inhabitants might look out and believe they are seeing all of existence. Just as we once mistook Earth for the center, then the sun, then our galaxy, then even our observable universe. The lesson keeps repeating, but on a larger and more humbling scale. The edge of what you can see is not always the edge of what is. Still, bubble universes should not be treated as fantasy copies of our world. They may have different histories, different amounts of matter, different expansion patterns, perhaps even different physical conditions depending on the deeper theory. Some might never form galaxies. Some might be empty and cold. Some might collapse or expand too quickly for complexity. And some, if the conditions allow, might unfold into rich cosmic histories of their own. But here is the haunting part. Even if countless bubble universes exist, most would be sealed away from us more completely than any locked room. A locked room at least shares your building. Another bubble may not share your causal future. It may be real, yet unreachable in principle. This challenges a habit buried deep in the human mind, the belief that what is real must someday be accessible. But nature may not obey that emotional rule. Some things may exist without ever becoming evidence for us directly. Science is cautious with such ideas because it must be. A claim that cannot be tested easily lives under suspicion. Yet caution is not the same as dismissal. Researchers have asked whether an ancient encounter between bubbles could leave a faint mark in the cosmic microwave background, the oldest light we can observe. No confirmed sign has settled the question, but the search itself shows how carefully the idea is handled, not as a story to believe, but as a possibility to constrain. And perhaps that is the most important thing bubble universes teach. They reveal a universe that may be bigger not only in size but in structure, a reality where beginnings may happen more than once, where what we call the Big Bang may be the beginning of our region rather than the beginning of everything, where cosmic history may be local rather than universal. For you, sitting inside this one bubble of time and matter, the thought can feel lonely at first. Other universes might exist, blossoming beyond all contact, each one with its own unreachable darkness. But there is also a quiet wonder in it. If our universe is a bubble, then everything you know, every star, every ocean, every breath, every memory, unfolds inside a fragile clearing in a much larger unknown. We are not outside the storm looking in. We are inside the calm that the storm once made possible. And maybe that is enough to make the familiar world feel strange again. Not smaller, not fake, not less meaningful, but suspended in a vastness so deep that even the word beyond begins to feel too small. Eternal inflation, when universe making never stops. A universe that makes more universes does not sound like astronomy at first. It sounds like a myth that learned the language of physics. Yet eternal inflation is one of those ideas that begins with a serious attempt to solve real problems and then grows into something almost impossible to hold in the mind. The basic story starts with inflation, the proposed moment in the very early cosmos when space expanded with extraordinary speed, stretching a tiny region into something vast, smooth, and nearly flat. This idea helps explain why distant parts of the observable universe look so similar, even though they seem too far apart to have exchanged light in the usual way, and why the large-scale shape of space appears so evenly balanced. But eternal inflation asks what happens if that early expansion was not a single event that ended everywhere at once. What if inflation stopped in some regions, allowing them to cool into ordinary, expanding universes filled with matter and radiation, while in other regions it kept going? What if the process that gave birth to our cosmic region was not a one-time beginning, but a self-renewing background, constantly creating new places where Big Bang-like histories can begin? This is the heart of eternal inflation. Universe making may not be something that happened once. It may be something that, in the larger picture, keeps happening. To understand why, you do not need heavy mathematics. You only need to follow the strange behavior of energy in empty space. During inflation, space is thought to have been filled with a special kind of energy, often associated with a field that can drive rapid expansion. In some models, this energy can decay, like a tense system relaxing into a lower state. Where it decays, inflation ends. The energy transforms into particles, heat, radiation, and the ingredients of a universe that can evolve more slowly. But if the decay is not uniform everywhere, then one region may exit inflation while nearby regions continue expanding. And because the still inflating regions grow so quickly, they can create more room for further decays to happen later. Each ended region is like a local beginning. Each continuing region keeps the engine alive. The result is not a neat sequence, but a vast uneven process, endings happening inside a background that does not fully end. This is why the word eternal appears, not necessarily because inflation had no beginning in the past, since that remains a difficult and debated question, but because in many versions it can continue indefinitely into the future. From inside one cooled region, inhabitants might look back and call their hot early state the beginning of the universe. But from the larger inflationary perspective, that beginning may be only a local transition, one pocket of calm where the storm released its energy. This idea is powerful, but it must be handled with care. Eternal inflation is not confirmed reality. It is not something a telescope has directly observed. It is a consequence that appears in some inflationary models, and its connection to the multiverse is one reason it is both fascinating and controversial. Scientists can test certain predictions of inflation by studying the cosmic microwave background, the ancient afterglow of the early universe, looking for patterns that match what inflation would leave behind. But testing eternal inflation itself is much harder, because the other regions it may produce could be forever beyond our ability to observe. This creates a tension at the edge of science. A theory may arise naturally from known ideas, and still generate consequences that are difficult to verify. And eternal inflation creates another problem, one that is less famous but deeply important. If the process makes enormously many regions, perhaps endlessly many, how do you count what is likely? In ordinary science, probability depends on comparing possibilities, but in an eternally inflating multiverse, where the number of regions may grow without limit, counting becomes strange. If everything that can happen happens many times, perhaps infinitely many times, then asking what is typical becomes difficult. This is called the measure problem, and it is not a small detail. It is one of the reasons eternal inflation remains a frontier rather than a finished answer. A theory that produces endless universes must also explain how to make meaningful predictions inside that endlessness. Without that, wonder can become fog. Still, the idea teaches something profound even before it is settled. It changes the image of creation. Instead of one cosmic birth followed by a single history, eternal inflation suggests a reality where beginnings may be local events, where what we call the Big Bang could be the moment our region became hot and structured, not necessarily the first moment of all existence. This does not make our universe less real. It makes it part of a possible wider process. It also changes how you think about time. We are used to asking what happened before the Big Bang, as if there must be one earlier chapter. Eternal inflation offers a different kind of answer. Perhaps beyond our beginning is not a simple before, but an inflating background where many beginnings occur, each sealed inside its own future. Some regions may form universes rich with galaxies, others may be empty, brief, or hostile to complexity. The larger process would not care which ones become beautiful. It would simply continue, making room, ending here, expanding there, releasing new histories like sparks from a fire that never fully burns out. And from inside our one spark, the thought is almost tender. Every galaxy we see, every atom in your body, every memory you carry, may belong to one local cooling of a much greater cosmic field. You are not watching universe making from outside. You are one of its consequences. If eternal inflation is wrong, then it still shows how far the human mind can push a scientific idea while remaining disciplined by evidence. If it is right, then reality is not a single birth certificate, but an endless maternity of space-time, producing regions that may never know one another. Either way, the lesson is not to believe too quickly, and not to shrink too quickly either. The universe may have begun for us in fire, but the deeper story may be that fire is not rare. Somewhere beyond observation, if eternal inflation truly continues, beginnings may still be happening, not as miracles, not as stories, but as physics unfolding in the dark, quietly making more reality than any one world can ever see. The fine-tuning mystery of our universe. The universe feels stable because you were born after its most dangerous balances had already succeeded. You open your eyes into a world where atoms hold together, stars burn for billions of years, planets can cool, carbon can form, water can remain liquid, and chemistry has enough patience to become biology. But none of this is as automatic as it feels. The fine-tuning mystery begins with a simple discomfort. Many features of our universe seem to sit within ranges that allow complexity, and if some of them had been very different, the universe might still exist. But it would not be a universe with galaxies, long-lived stars, heavy elements, planets, or minds capable of asking questions. This does not mean the universe was intentionally adjusted, and it does not prove design, destiny, or a hidden hand-turning cosmic dials. Fine-tuning is not a conclusion. It is the name of a problem. It points to the strange fact that the life-permitting universe we inhabit depends on a deep cooperation between physical quantities that did not have to feel obvious from the start. Take gravity. If gravity were much stronger on cosmic scales, matter could clump too aggressively, stars might burn too quickly, and the universe could become a violent place with less time for stable complexity. If gravity were much weaker, matter might struggle to gather into galaxies and stars at all. The issue is not that one tiny change instantly destroys everything in every model. The issue is that the universe we know depends on gravity being balanced with other features in a way that allows structure to grow without collapsing too soon or spreading too thin. Or think about the forces inside atomic nuclei. Stars do not shine by magic. They shine because nuclear reactions can convert simple elements into heavier ones and release energy slowly enough to illuminate worlds for immense periods of time. The carbon in your body was not placed there ready-made. It was forged through stellar processes that depend on nuclear physics being arranged in a very particular way. Carbon formation inside stars involves a special excited state of the carbon nucleus, often called the Hoyle state, which makes it possible for stars to build carbon efficiently from helium. Without that kind of pathway, the chemistry of life as we know it would be far harder to imagine. The oxygen you breathe, the calcium in your bones, the iron in your blood, the carbon chains behind biology, all of these are consequences of a universe where stars can act as slow furnaces instead of brief explosions or useless lamps. Fine-tuning also appears when we look at expansion. The early universe had to expand fast enough not to collapse immediately, but not in a way that prevented matter from gathering later. The tiny irregularities in the early cosmos had to be large enough to seed galaxies, but not so large that everything became too chaotic. Even empty space itself enters the mystery. The energy associated with space, often discussed through dark energy or the cosmological constant, appears small enough that galaxies had time to form before cosmic expansion became dominant. If that repulsive effect had overwhelmed structure too early, matter could have been driven apart before stars and galaxies matured. Again, the point is not to say we fully know all possible universes, or that life could only look exactly like us. The point is that the universe's ability to produce complexity seems to depend on relationships between many features, not on one isolated miracle. This is what makes the mystery so difficult. You cannot simply move one dial while pretending the others stay emotionally unchanged. Physics is a web. Change the strength of one force, and atoms may change. Change particle masses, and chemistry may change. Change expansion, and galaxies may never form. Change nuclear reactions, and stars may fail to make the ingredients later needed by planets. The universe is not a machine with one lucky button. It is more like an orchestra where the possibility of music depends not only on each instrument, but on the way they remain in tune together. Scientists approach this mystery in several ways, and honesty requires keeping them separate. One possibility is that the constants are not truly free to vary. A deeper theory may one day show that they could not have been otherwise. In that case, what looks fine-tuned to us may be the visible surface of a necessity we do not yet understand. Another possibility is that there are many different cosmic regions or possible universes with different properties, and we naturally observe one compatible with complexity because no observer could arise in the lifeless ones. Another possibility is that our understanding of what counts as life-permitting is too narrow, and that forms of complexity unlike ours could exist under conditions we have not learned to imagine. None of these answers is complete. Each one opens more questions than it closes, and that is why fine-tuning remains powerful. Not because it gives an easy explanation, but because it refuses to let the universe feel ordinary. It makes you realize that your existence is not resting on a single fact, but on a chain of physical permissions. Stars had to live long enough, elements had to form, planets had to remain stable, chemistry had to become rich, time had to be generous, and somewhere inside that generosity, matter learned to remember, fear, love, calculate, and wonder. You are not separate from the fine-tuning mystery. You are one of its consequences. Your body is made from the same cosmic balances the question is about. Your thoughts are not floating above physics. They are physics becoming inward. Physics discovering that the conditions allowing stars also allowed sadness, music, language, and the quiet ache of asking why there is something rather than nothing. So the fine-tuning mystery should not be treated as a slogan. It should be treated as a doorway. Step through it carefully, and you do not find a simple answer waiting on the other side. You find a deeper kind of humility, the recognition that the universe did not merely make room for matter, it made room for meaning. And whether that room exists by necessity, chance, deeper law, or a wider cosmic landscape, the fact remains astonishing. The laws did not have to feel kind, the stars did not have to become fertile, the darkness did not have to allow eyes, yet here you are, a fragile arrangement of atoms, listening inside a universe balanced well enough to let itself be questioned. The Anthropic principle. Why we see a life-friendly universe. You do not observe a life-friendly universe from the outside. You observe it from the only kind of place where observers could ever appear. That single sentence is the quiet heart of the Anthropic principle. And at first, it may sound almost too obvious to matter. Of course, we see a universe compatible with life, because if it were not compatible with life, we would not be here to see it. But hidden inside that simple thought is one of the most misunderstood ideas in cosmology. The Anthropic principle does not say the universe was made for humans. It does not say consciousness controls physics. It does not prove purpose, design, or destiny. It begins with a colder and more disciplined insight. Every observation is filtered by the conditions required for an observer to exist. You cannot find yourself in a universe where no chemistry can support bodies, no stars can provide energy, no stable environments can last long enough for evolution, no atoms can form brains, and no time exists for memory to grow. Such a universe might be possible in theory, but it would be silent. It would have no witnesses. So when we look around and notice that the universe permits life, we must be careful before calling it a miracle. We are not randomly sampling all possible realities from the outside. We are a product of this reality, looking back from within the narrow window that allowed us to form. This is what makes the Anthropic principle useful. It reminds you that your viewpoint is not neutral. It is selected. It is biased by your own existence. A good way to feel this is to think about time. Why do we live in a universe old enough to contain heavy elements, planets, and long-lived stars? Because observers like us could not appear too early. In the first moments after the Big Bang, there were no rocky planets, no oceans, no carbon-based organisms, no biology waiting in the fire. The universe needed generations of stars to form, burn, enrich space with heavier elements, and seed later worlds with the ingredients of life. So the age of the universe we observe is not just a random number on a cosmic clock. It is partly explained by the fact that we could only emerge after the universe became old enough to build us. But we also do not appear infinitely late, after stars have all burned out and useful energy has faded into darkness. We find ourselves in a cosmic era where stars still shine, planets still orbit, and complexity still has room to breathe. The Anthropic principle turns this into a selection effect. We observe a time compatible with observers because incompatible times contain no observers to ask why they are empty. The same logic applies to place. You do not find yourself inside the core of a star, or drifting in deep intergalactic emptiness, or crushed inside a black hole. Not because the universe avoids such places, but because those places do not allow beings like you to sit quietly and ask questions. You find yourself on the surface of a stable planet, around a long-lived star, in a galaxy with enough heavy elements, because that is the kind of environment that can produce someone capable of noticing the environment. This does not make Earth central. It makes Earth selectable. It is like waking up in the one room of a vast building where the air is breathable, then feeling astonished that you are not in a room filled with poison. The surprise is understandable, but the observation already contains the explanation. Only the breathable room can contain a waking witness. In cosmology, this becomes especially important when people discuss fine-tuning. If there are many possible universes, or many cosmic regions with different conditions, then observers would naturally arise only in the rare regions compatible with observers. This does not prove that such a multiverse exists. It only shows how a multiverse, if real, could make our life-friendly conditions less shocking without saying they were chosen for us. The Anthropic principle is not the whole answer. It is a filter on what any answer must respect. Used carefully, it prevents false surprise. Used carelessly, it becomes a way to stop thinking. That is the danger. If every mystery is dismissed by saying, "We see it this way because otherwise we would not be here," then curiosity dies too early. The Anthropic principle can explain why our observations must be compatible with our existence, but it does not automatically explain why the deeper laws exist, why there is a universe at all, or why the range of possible conditions is what it is. It is a lens, not a final theory. It helps clean the glass through which we look, but it does not replace the landscape beyond it. There is also a stronger version of anthropic thinking, sometimes phrased as if the universe must allow life, or is somehow compelled to produce observers. That stronger language is far more controversial, because it begins to sound less like a selection effect and more like a cosmic purpose. The safer, more scientific version is humbler. Our observations are conditioned by the fact that we are observers. This humility is what gives the idea its power. It teaches you that the universe you see is not simply the universe as it is, but the universe as seen from a rare position inside it. You are not standing nowhere. You are standing in a biological, planetary, stellar, and cosmic context that had to exist before your questions could. And suddenly, the simple act of looking around becomes strange. The sky is not just beautiful. It is compatible. The laws are not just abstract. They are the background permissions of your breath. The age of the cosmos is not just ancient. It is ancient enough. The planet beneath you is not just home. It is one of the few kinds of places where the universe can become aware of itself. So the Anthropic principle does not tell you that reality was built for you. It tells you something quieter and perhaps more profound. You can only see a universe that was able to grow eyes. And once you understand that, your existence feels neither guaranteed nor accidental in the ordinary sense. It feels conditional, balanced on a chain of requirements so deep that every ordinary moment becomes less ordinary. You are not proof that the universe had you in mind. You are proof that, at least here, the universe allowed mind to appear. Why the multiverse may be impossible to prove. The hardest thing about the multiverse may not be imagining it, but proving it without ever being allowed to step outside our own universe. Science is powerful because it does not ask us to believe every beautiful idea. It asks for contact, a measurement, a signal, a prediction that could have failed, a mark left on the world that separates a real theory from an elegant story. And this is exactly where the multiverse becomes difficult. If another universe is truly separate from ours, if it cannot send light to us, cannot exchange particles with us, cannot leave any trace in our instruments, then it may be real in some wider sense and still be unreachable by science in the strongest sense. That is the uncomfortable border we have to face. The multiverse is not automatically nonsense, but neither is it automatically established just because certain theories point toward it. It lives in a tense region where physics, philosophy, and humility meet. To prove something, you normally need a way for it to affect what you can observe. A planet pulls on its star, so we infer it. Dark matter bends light and shapes galaxies, so we study its effects even without seeing it directly. Black holes reveal themselves through gravity, radiation, and the motion of nearby matter. Indirect evidence is still evidence when the invisible thing leaves fingerprints. But what if other universes leave no fingerprints at all? What if they are not hidden behind dust or distance, but sealed behind causal separation? The observable universe is already limited by light, time, and expansion. We cannot see everything that exists even within our own cosmic history, because some regions are beyond what can ever reach us. A separate universe would be an even deeper challenge. It might not simply be too far away. It might belong to a region of reality with no shared channel of communication. In that case, no telescope becomes large enough. No spacecraft becomes fast enough. The problem is not technology. It is contact. This is why some critics argue that certain multiverse ideas may fall outside testable science if they make no unique predictions we can check. A theory that explains everything after the fact but risks nothing before the evidence arrives becomes hard to distinguish from imagination. Science needs vulnerability. It must be possible, at least in principle, for the world to say no. If a multiverse model can absorb any observation and still remain unchanged, then it loses scientific sharpness. But there is another side. Some defenders argue that the multiverse should not be judged by whether we can observe other universes directly, because science often accepts unobservable entities when they are part of a theory that explains observable facts better than its rivals. We do not see quarks with naked eyes. We do not see space-time curvature itself. We infer deep structures through the success of the theories that require them. In this view, a multiverse could become scientifically respectable if it emerges from a broader theory that makes clear predictions in our universe and survives difficult tests. The other universes would not be proven one by one. They would be accepted as part of the best explanation, the way unseen interiors of stars are accepted through a theory that also predicts what we can measure. This is the key distinction. Direct proof may be impossible, but indirect support might not be. The question is whether the multiverse is an unavoidable consequence of a well-tested theory, or an optional add-on used to make mysteries feel less mysterious. that difference matters enormously. For example, some versions of inflation suggest that regions beyond ours may exist, but testing the larger picture requires looking for signatures. Inflation lives in the cosmic microwave background and the distribution of structure. Some quantum interpretations imply branching worlds. But if all interpretations make the same experimental predictions, choosing between them becomes less like a simple experiment and more like comparing explanatory frameworks. Some ideas from high-energy theory suggest a landscape of possible physical conditions, but connecting that landscape to testable predictions remains deeply challenging. The problem is not that scientists refuse wonder. The problem is that the universe may not give us enough evidence to turn certain kinds of wonder into knowledge. And this is where the multiverse becomes psychologically dangerous. It is easy to love an idea so much that you start treating possibility as possession. You say, there are other universes, when the honest sentence is, some serious theories may allow or suggest other universes. That difference is not small. It is the difference between education and mythology. A good mind must be able to stand in uncertainty without decorating it too quickly. The multiverse may be true, it may be false. It may be partly true in a way our current language handles badly, or it may be replaced by a deeper theory that explains the same puzzles without multiplying realities. For now, its greatest weakness is also its greatest lesson. Reality may be larger than our ability to confirm it. That thought should not make science feel smaller. It should make science feel more disciplined. Science is not the claim that only measurable things exist. It is the method by which we separate what we can know from what we can merely imagine. There may be truths forever outside our horizon, but if they never touch us, they remain outside our evidence. And perhaps that is the most honest kind of awe. Not pretending to know, not refusing to ask, but recognizing the shape of the wall. The multiverse may be impossible to prove because proof requires a bridge, and some realities, if they exist, may have no bridge to ours. Still, the question itself has value. It forces us to ask what counts as explanation, what counts as evidence, and how far a scientific theory can reach before it becomes philosophy. It reminds us that knowledge is not the same as possibility, and humility is not the same as surrender. So, the multiverse remains suspended, too serious to dismiss as fantasy, too unconfirmed to preach as fact. It waits at the edge of proof like a coastline hidden by fog, perhaps real, perhaps unreachable, perhaps only the shape our best theories cast when they face the unknown. And you, standing on this side of the horizon, are left with a quieter truth. The universe may not owe us final answers, but the search for them can still teach us how to think with care. The ultimate ensemble, every possible universe. There is a version of the multiverse so extreme that it does not merely ask whether other universes exist. It asks whether existence itself is the same thing as possibility made perfectly consistent. This is called the ultimate ensemble, and it is one of the most radical ideas ever placed at the edge of cosmology. It does not begin by imagining another Earth, another timeline, or another bubble of space beyond our cosmic horizon. It goes deeper than that. It asks whether every possible self-consistent mathematical structure might exist as its own kind of physical reality. Not every dream, not every fantasy, not every story a human mind can invent. A universe where contradictions are allowed, where rules break themselves, where one thing is both completely true and completely false in the same way, would not count. The ultimate ensemble is stranger and more disciplined. It suggests that any reality whose rules are internally coherent may not simply be an abstract idea sitting in a mathematician's notebook. It may be a universe from the inside. To understand why this is so disturbing, begin with something ordinary. Your world feels physical because it has weight, distance, heat, motion, resistance. But physics describes all of those experiences through patterns. A falling object follows a pattern. Light follows a pattern. Atoms bond according to patterns. Even the flow of time and the shape of space are described through relationships that can be expressed mathematically. The more deeply science studies nature, the less the universe looks like a pile of objects, and the more it looks like a structure of relations. Things are not just there, they behave, they follow rules, they fit into a hidden order. The ultimate ensemble takes this observation and pushes it to its furthest possible conclusion. Perhaps mathematics does not merely describe reality from the outside. Perhaps reality is mathematical structure experienced from the inside. In that view, our universe is not made real by some extra substance poured into equations like water into a cup. It is real because the structure exists, and beings inside that structure experience it as a world. This does not mean your life is a set of numbers in any shallow sense. You do not feel like mathematics when you are afraid, tired, moved by music, or watching sunlight cross a wall. But the processes that make those experiences possible may be part of a deep pattern, a rule-governed system rich enough to contain memory, awareness, and the illusion of solidity. If another structure had different rules, its inhabitants, if it could contain inhabitants at all, would not necessarily see our kind of space, our kind of matter, or our kind of time. Their physics might be unrecognizable. Their reality might not contain stars or atoms in any familiar sense. It might have dimensions, relationships, and forms of change that human imagination cannot turn into images. And yet, from within, if consciousness could arise there, it might feel just as real to itself as this universe feels to you. This is what makes the ultimate ensemble different from gentler multiverse ideas. It is not simply more of our universe, and it is not simply different regions with different settings. It is the proposal that all possible rule systems may be equally real, and that our universe is only one member of an unimaginably larger collection. But here is where careful thinking matters. The ultimate ensemble is not established science. It is a speculative philosophical cosmological proposal, associated especially with Max Tegmark's mathematical universe hypothesis. It has not been proven. Many physicists and philosophers remain skeptical, partly because it is difficult to test, and partly because it raises deep problems about probability. If every possible structure exists, why do we find ourselves in this one? How do you count possible realities? Are simple structures more likely than complex ones? What does likely even mean when the collection may be infinite? These are not small objections. They are central wounds in the idea. A theory that says everything possible exists must still explain why observers should expect to see a universe like ours. Orderly, mathematically elegant in many places, complex enough for life, yet not so chaotic that prediction becomes impossible. Without a way to make meaningful expectations, the ultimate ensemble risks becoming too large to guide us. It becomes a library with every coherent book, but no clear reason why you woke up reading this page. Still, the idea has a strange power because it transforms the oldest question of all. Why is there something rather than nothing? Instead of saying reality began from a special event or was selected from nothingness, the ultimate ensemble suggests that nothingness may have been the wrong starting point. If every consistent structure exists, then existence is not a rare accident that needs to be switched on. It is the full collection of what can be. In this view, our universe does not need to be chosen from outside. It exists because it is one coherent possibility among all coherent possibilities. That sounds elegant, almost too elegant, but it comes at a cost. It removes the comfort of uniqueness. It says, the deepest layer of reality may not care which universe feels central from within. Every structure that can contain observers may have its own center, its own inside, its own beings asking why their world has the rules it does. And this leads to a quiet psychological shock. If the ultimate ensemble were true, then reality would be far larger than space, larger than time, larger even than physics as we know it. Our universe would be one language in an infinite grammar of possible worlds. You would not be living in the only book. You would be living in one readable sentence inside a library without walls. But this does not make your life meaningless. It changes where meaning must be found. Meaning would not come from being the only universe, or the most important universe, or the final universe. It would come from the fact that inside this structure, experience happens. Pain matters because it is felt. Love matters because it changes the inner life of beings who can suffer and remember. Truth matters because some patterns correspond to the world you actually inhabit, while others do not. Even in an ultimate ensemble, you are not free to live in every possibility. You are bound to this one, this physics, this body, this time, this chain of consequences. The grand collection may be infinite, but your awareness is local. You do not wake up as all possible selves. You wake up here, inside one narrow stream of reality, where choices still carry weight because they shape the only world available to your hands. And perhaps that is the most human lesson hidden inside this most inhuman idea. The ultimate ensemble stretches existence until the mind almost loses its grip. But it also returns you to the smallness of the present with new tenderness. If every possible consistent universe exists, then this moment is not less real because others may also be real. A candle does not become dimmer because stars exist. A single voice does not become silent because 1,000 languages can be spoken. This universe, whether unique or one among all possible structures, is the one in which you are awake. It is the one where matter became memory, where law became life, where a pattern learned to ask what patterns are. So the ultimate ensemble does not give you a simple answer. It gives you a vertigo of possibility, and then asks whether you can still live carefully inside one reality. Maybe all possible universes exist. Maybe only this one does. Maybe the truth is stranger than both. But tonight, beneath that uncertainty, one fact remains close enough to touch. Whatever reality ultimately is, it has become aware of itself here, through you, for a brief and luminous moment. What the multiverse really means. The multiverse does not really mean many copies of you. It means the word universe may have been too small for what reality could be. That is the first thing to understand, because the word has been stretched by movies, internet theories, and dramatic storytelling until it often feels like a glowing doorway to endless alternate lives. But in serious thought, the multiverse is not one single theory and not one single place. It is an umbrella name for several different possibilities that all share one unsettling idea. What we call the universe may not be the full extent of existence. It might be one observable region inside a larger space. It might be one cosmic domain produced by a deeper process. It might be one branch of a quantum description. It might be one solution among many possible physical arrangements. These ideas are not identical, and treating them as the same creates confusion. The multiverse is not a single map with other worlds neatly labeled. It is a family of questions about whether our reality is complete, isolated, unique, or only local. And that distinction matters, because the real power of the multiverse is not that it gives easy answers. It is that it challenges the assumptions hidden inside ordinary language. When you say the universe, you usually mean everything. All space, all matter, all time, all events, all galaxies, all possible places. But in cosmology, the word can become more subtle. Sometimes universe means the observable universe, the region whose light has had time to reach us. Sometimes it means the total connected space-time of which our observable region is only a part. Sometimes, in multiverse discussions, it means one domain with its own history, conditions, or effective laws. So before the multiverse can be understood, the word universe itself has to loosen. It stops being a simple container and becomes a question of boundaries. What can affect us? What can we observe? What shares our physical history? What belongs to the same space-time? What is only inferred by theory? These boundaries do not always line up. Something can be beyond observation and still be part of the same larger cosmos. Something can be mathematically implied and yet not experimentally confirmed. Something can be physically possible and still forever unreachable. The multiverse lives inside these distinctions. It asks whether reality is divided not by walls, but by horizons, causal limits, different physical states, or incompatible descriptions. This is why it is both scientifically serious and philosophically dangerous. Serious, because it can arise from attempts to solve real problems in physics and cosmology. Dangerous, because it can easily become a place where people hide unsupported claims. A careful mind has to hold both truths at once. The multiverse is not proven fact, but it is also not merely fantasy. It is a set of proposals that appear when our best ideas are pushed beyond the region we can directly test. That is why it attracts both physicists and philosophers. It sits at the border between explanation and evidence. In one sense, the multiverse means humility. It reminds us that human observation has limits. For most of history, we mistook our local view for the whole. The village became the world, the Earth became the center, the Milky Way became the universe, and the visible cosmos became the edge of reality. Each expansion of knowledge taught the same lesson. The boundary of perception is not necessarily the boundary of existence. The multiverse extends that lesson to its most extreme form. It says, even the entire observable cosmos, with all its galaxies and ancient light, might be only one accessible patch of something larger. But in another sense, the multiverse means discipline. Because if an idea lies partly beyond observation, it must be treated with extra care, not less. You cannot point to mystery and call it evidence. You cannot turn possible into true just because it feels profound. The multiverse forces science to ask a difficult question. When does a theory earn belief? Is it enough that it explains what we see? Must it also predict something new? Can we accept unobservable consequences if the theory producing them succeeds elsewhere? Or must every claim, no matter how elegant, remain suspended until contact with evidence becomes possible? These are not side questions. They are central to what the multiverse really means. It is not only about other worlds. It is about the rules of knowing. It tests the honesty of wonder. And then, beneath the scientific debate, the idea reaches into the human sense of meaning. If our universe is not the whole, does it become less important? If reality contains domains we will never touch, does our life shrink? The answer depends on what you think importance means. If meaning requires cosmic centrality, then every scientific discovery has been a wound. Earth is not central. The sun is not central. Our galaxy is not central. Our observable universe may not be central either. But if meaning comes from experience, relation, consciousness, and consequence, then the multiverse does not erase it. It only removes the illusion that importance must equal size. A life can be small and still be real. A moment can be brief and still be deep. A universe can be local and still contain everything that has ever mattered to the beings inside it. The multiverse, understood properly, does not tell you that everything is meaningless because there may be more. It tells you that reality may be layered and that meaning must be found from within the layer where you are awake. It also changes the way we think about laws. We often speak of the laws of physics as if they are carved into the foundation of all possible existence. But multiverse thinking raises the possibility that some features of our universe may be local conditions rather than universal necessities. The laws we experience may be absolute for us, yet not necessarily the only way a coherent reality could operate. This does not make science weaker. It makes science more careful. It asks whether what we call fundamental is truly fundamental, or only fundamental inside our domain. That question is not an escape from physics. It is a deeper demand placed on physics. It asks for a theory that can explain not only how this universe works, but why this set of workings exists at all. And maybe that is the deepest meaning of the multiverse. It shifts the question from what is in the universe to why this kind of universe. It turns reality from a finished stage into a problem of selection, structure, and perspective. Why these conditions? Why this history? Why these observable limits? Why a cosmos where atoms can form, stars can live, and minds can eventually ask about the whole? The multiverse may one day help answer some of those questions, or it may be replaced by a better idea. But even now, it teaches a form of intellectual maturity. It asks you to stay open without becoming gullible, skeptical without becoming small, amazed without abandoning evidence. So what does the multiverse really mean? It means reality may be larger than the universe we can see. It means the word everything may depend on where you stand. It means our cosmos might be one chapter, not necessarily the whole book. It means science may reach places where direct proof becomes difficult and where honesty matters more than certainty. And finally, It means that you are living inside a mystery that is not reduced by being questioned. The room around you remains real. The stars remain real. Your breath remains real. But behind all of it, the larger possibility waits. That existence may not be a single voice speaking one cosmic sentence, but a vast silence capable of holding many realities while you listen from one of them, trying carefully to understand what the word real was always trying to say. Why scientists even consider other universes. Scientists do not consider other universes because the idea is dramatic. They consider them because some of our best questions refuse to stay inside one universe. That is the first correction to make. The multiverse did not enter serious conversation because physicists wanted a grander myth, or because ordinary cosmology felt too small, or because science secretly needed science fiction. It appeared because certain problems, when followed carefully, seem to point beyond the region we can observe. This does not mean other universes are proven. It means that the idea sometimes emerges as a consequence of trying to explain things we already see. The smoothness of the early universe, the apparent specialness of physical constants, the strange structure of quantum theory, the possibility that the laws we know are not the only mathematically consistent arrangement nature could allow. Science has a long history of accepting that reality may be larger than immediate perception. No one has seen the inside of a star directly, yet stellar physics tells us what happens there through light, heat, spectra, and models that successfully predict what we observe. No one has held dark matter in their hand, yet galaxies and gravitational lensing suggest that something unseen has mass. No one sees space-time curvature the way one sees a stone. Yet general relativity earns trust because it makes accurate predictions about gravity, light, clocks, and cosmic motion. This is the pattern. Scientists do not need to touch something directly if a theory that includes it explains the visible world better than alternatives and risks being wrong in specific ways. The question is whether other universes can ever earn that kind of status. The first reason scientists consider them comes from inflation, the idea that the early universe underwent an extremely rapid expansion. Inflation was proposed to solve real puzzles. Why the universe looks so uniform in regions that seem too far apart to have shared information, why space appears so close to flat on large scales, and why the early irregularities had just the right kind of smallness to grow into galaxies rather than chaos. In some versions, inflation is not a clean switch that turns off everywhere at once. It may end in some places while continuing in others, naturally producing separate regions with their own cosmic histories. Scientists do not start by saying, "Let us invent other universes." They start by asking how inflation works, and then some models answer, "It may produce more than one universe-like domain." That is a very different kind of claim. It is not a wish. It is a possible consequence of a mechanism already introduced to explain observable features of our own cosmos. The second reason comes from quantum mechanics. Quantum theory describes nature with extraordinary success, but it also leaves us with the measurement problem. Before measurement, systems are described in terms of possibilities, yet experience gives us only one definite result. Some interpretations say the possibilities collapse into one outcome. Others, like the many worlds interpretation, say the underlying quantum description never collapses, and that what we experience as one result is only one branch of a larger structure. Again, scientists who consider this are not simply multiplying worlds for entertainment. They are asking whether adding a mysterious collapse rule is less elegant than accepting a larger reality where all outcomes remain part of the theory. You may disagree with that answer, and many scientists do, but the reason it is considered is serious. Quantum mechanics works too well to ignore, and its meaning remains unsettled. The third reason is fine-tuning. Our universe seems to have physical conditions that allow long-lived stars, stable atoms, rich chemistry, and eventually observers. One way to explain that is to search for a deeper law showing these conditions could not have been otherwise. Another way is to consider whether many domains with different conditions exist, and observers naturally arise only in those where complexity is possible. This does not prove a multiverse. It does not even prove that fine-tuning must be explained this way, but it gives scientists a reason to take the idea seriously as one possible explanation among others. If there is only one universe, the life-friendly nature of its conditions can feel like a strange coincidence or a clue to deeper necessity. If there are many possible domains, the surprise changes shape. We should not be shocked to find ourselves in one compatible with our existence, because incompatible domains would have no one inside them asking questions. The fourth reason is theoretical unity. Physicists often search for deeper frameworks that can connect separate forces and explain why particles and constants have the values they do. Some high-level theories suggest not one unique physical world, but a large space of possible solutions, each with different effective laws or conditions. Scientists consider other universes partly because the mathematics of these theories may not point to a single cosmic outcome. But here, caution becomes essential. A theory can be mathematically rich and still not describe reality. Beauty is not evidence, elegance is not confirmation. A landscape of possible universes is not the same as a discovered multiverse. This is why the best scientists speak carefully. They do not say, other universes definitely exist. They say, certain theories may imply them, and we must ask whether those theories can be tested through what they predict here. That is the core of the issue. Other universes, if completely disconnected from ours, may never be observed directly. So scientists must ask whether the theory that predicts them also makes testable predictions inside our own observable universe. Does it explain patterns in the cosmic microwave background? Does it predict features of particles, gravity, or structure formation? Does it solve old problems without creating worse ones? Does it make the world more understandable? Or does it merely move the mystery behind a curtain? These questions are why the multiverse remains controversial. Some scientists see it as a natural consequence of serious physics. Others worry it weakens science by placing too much weight on things that may never be tested. Both concerns matter. The multiverse is not a simple belief. It is a stress test for what explanation means. It asks how far science can extend beyond observation while still remaining science. And perhaps that is why the idea is so important, even if it turns out to be wrong. It forces us to examine the hidden architecture of knowledge. We are used to thinking that science only moves from observation to conclusion, but in reality, it often moves through a triangle: observation, theory, and prediction. Observations create puzzles. Theories attempt to explain them. Predictions test whether the explanation has real contact with the world. Other universes may sit at the far edge of that triangle. They may be consequences we cannot touch directly, but if the theories that require them keep succeeding in testable ways, the idea gains weight. If those theories fail, the idea loses force. This is how careful science protects itself from fantasy. It does not forbid large ideas. It demands that large ideas pay rent in evidence. So why do scientists even consider other universes? Because our own universe raises questions so deep that one universe may not be enough to explain why it looks the way it does. Because inflation, quantum theory, fine-tuning, and deeper physics all open doors that do not close easily. Because science has learned, again and again, that the visible world is not always the whole world. But also because honest scientists know the difference between considering and knowing. Other universes may exist. They may not. They may be real but forever unreachable. They may be replaced by a more elegant theory that explains everything without them. For now, the multiverse remains a serious possibility, not a settled fact. A question held at the edge of evidence. And maybe that is exactly where the human mind grows. Not in pretending certainty, and not in refusing wonder, but in standing before a universe that may be only one room in a much larger house, listening carefully for clues in the walls, knowing that the silence itself may be part of the lesson, the difference between parallel universes and alternate timelines. A timeline is not another place you can point to in the sky. It is a story about how events connect. And that is why people so often confuse it with a parallel universe. The two ideas sound almost identical in everyday conversation, but they are not the same. A parallel universe usually means a separate realm of reality, another cosmic region. another branch of quantum history, another domain with its own contents, perhaps even its own physical conditions. An alternate timeline, on the other hand, means a different sequence of events, a version of history where something happened differently, and everything after it unfolded along another path. One is about where reality may exist. The other is about how reality may have unfolded. They can overlap in some theories and stories, but they do not have to. This distinction matters because without it, the multiverse becomes a blur of movie logic, where every lost chance becomes a glowing world somewhere, every regret becomes a destination, and every historical question becomes a portal. Real science is more careful. If a parallel universe exists as a distant region of space, it might not be an alternate timeline at all. It could have no connection to our history. It may not contain Earth, humans, or anything familiar. It may simply be another part of a much larger reality, with different arrangements of matter or different conditions. Calling that an alternate timeline would be misleading, because it is not a modified version of our story. It is its own story. Likewise, an alternate timeline in fiction often begins with one changed event. A war ends differently. A person survives. A decision is reversed. A discovery happens earlier, and the future grows from that altered route. This is powerful because human beings understand life through causality. We know how one small action can change everything around it. But in physics, alternate timelines are not automatically created by human choices in the simple dramatic way fiction suggests. Time is not known to be a branching tree where every decision creates a fully accessible new road. That image is emotionally compelling, but it is not established fact. The closest serious scientific cousin is the quantum branching idea found in the many worlds interpretation, where different outcomes of quantum events may correspond to different branches of the universal wave-like description. But even there, the branches are not ordinary roads, and they are not known to be reachable. They are not timelines in the cinematic sense of traveling backward, changing one event, and stepping into a new future. They are separated histories that no longer interfere in ordinary experience. This is why language matters. A parallel universe can be spatial, cosmological, quantum, mathematical, or theoretical. An alternate timeline is specifically historical. It depends on the idea of a shared past that diverges. If there was never a common past, then it is not really alternate. It is simply other. Think of two books. If one book begins with the same first chapters as yours, and then changes at chapter 10, that feels like an alternate timeline. If another book has different characters, different rules, different geography, and no shared origin, it may be parallel in the sense of existing beside your story, but it is not an alternate version of your story. The confusion becomes stronger because fiction blends them for drama. A superhero enters a parallel universe where history changed. A scientist opens a portal to a world where one empire won, one invention failed, or one person never died. These are alternate histories framed as parallel worlds. There is nothing wrong with that as storytelling, but science asks sharper questions. What makes the other world real? Does it share our laws? Does it share our past? Is it physically connected to us? Was it produced by quantum branching, cosmic inflation, simulation, or just imagination? Each answer creates a different kind of other reality. The alternate timeline idea also raises a deeper problem. What does it mean to change the past? In most known physics, the past is not treated like a document you can edit from the outside. Time travel into the past, if it is possible at all, would face severe paradoxes and constraints. If you go back and prevent the event that caused you to travel, the story breaks. Some speculative solutions suggest history might be self-consistent, meaning anything you do in the past was always part of the past. Others suggest a changed event might create or enter another branch rather than rewrite your original history. But these are speculative frameworks, not established travel instructions. The important point is this: alternate timelines are often about causality and memory. They ask how the present would differ if the past had taken another route. Parallel universes are broader. They ask whether existence contains other domains beyond the one we inhabit. One idea is historical. The other is ontological. One wonders, What if events had gone differently? The other wonders, what else exists? And when you separate them, both become more interesting. Parallel universes stop being only copies of our world and become a question about the architecture of reality. Alternate timelines stop being only fantasy and become a way to think about contingency. How fragile the present is. How dependent your life is on sequences that could have been otherwise. A different meeting, a delayed train, a storm, a mutation, an asteroid, a silence, a sentence spoken too late. History is full of turning points, but not all turning points need literal universes to matter. In your mind, alternate timelines already exist as counterfactuals. They are the lives you measure against this one, the futures you almost entered, the versions of yourself that feel near but unreachable. Science may not confirm them as physical worlds, but psychology confirms their emotional power. You can be shaped by a timeline that never happened. You can grieve a future that was only possible. You can feel the weight of a choice because the mind understands that reality narrows. That is why alternate timelines fascinate us. They are not only cosmic ideas, they are personal mirrors. Parallel universes, by contrast, humble us in a different way. They suggest that reality may not be centered on our story at all. There may be other domains that do not care about our history, do not branch from our decisions, do not contain our faces, and do not exist to answer human regret. They would be parallel, not because they are versions of us, but because they are independent expressions of existence. This is less emotionally comforting, but more scientifically honest. The universe, if it is larger than we know, may not be filled with alternate biographies. It may be filled with forms of reality that have nothing to do with us. And perhaps that is the deepest difference. Alternate timelines make the cosmos feel intimate, as if reality is endlessly rehearsing your life with variations. Parallel universes make the cosmos feel vast, as if your life is one small local flame among possibilities that may not resemble you at all. Both ideas stretch the mind, but in opposite directions. One turns inward toward choice, regret, identity, and history. The other turns outward toward space, structure, law, and existence beyond contact. To confuse them is to lose the lesson each one offers. A parallel universe asks you to accept that reality may be larger than the world you can observe. An alternate timeline asks you to accept that the life you know is the result of fragile sequences, and that different outcomes are conceptually meaningful even if they are not physically accessible. So when you hear these phrases, do not let them blur into one glowing fantasy. Ask what is really being claimed. Is it another region? Another branch? Another history? Another set of laws? Another possible outcome? The answer changes everything. And maybe, in the end, the difference teaches something quiet about your own existence. You do not need to know whether alternate timelines are physically real to understand that your choices carry weight. You do not need to prove parallel universes to understand that your world may not be the whole of reality. Between those two ideas, one personal and one cosmic, you find yourself exactly where human thought often lives, standing inside one history, beneath one sky, wondering how many other ways existence could have been, and how carefully you should live inside the one that became real. Why the universe may be bigger than we can ever see. The sky does not end where our telescopes stop seeing. It ends only where the oldest light has finally run out of time to reach us. This is the quiet mistake many people make when they think about the size of the universe. They imagine the observable universe as a kind of cosmic container, a sphere filled with galaxies, surrounded by nothingness beyond its edge. But the edge of what we can observe is not a physical wall. It is not the border of existence. It is a limit created by time, light, and expansion. The universe is about 13.8 billion years old. So at first it seems natural to think we should see only 13.8 billion light years in every direction. But space itself has been expanding while light has been traveling through it, stretching the distance between us and the places that emitted that ancient light. That is why the observable universe reaches much farther than the simple age of the cosmos would suggest, extending roughly 46 billion light years in every direction. This does not mean anything broke the speed of light in the usual sense. Galaxies were not flying through space faster than light like stones thrown from an explosion. Rather, the space between distant regions expanded, increasing the distance while the light was still on its way. So when you look deep into space, you are not seeing a solid boundary. You are seeing a horizon, the farthest region from which light has had enough time to arrive. Beyond that horizon, there may be more galaxies, more dark matter, more empty space, more structure, perhaps vastly more than we can ever observe. We do not know the full size of the entire universe. It may be finite but so large that its curvature is too subtle for us to detect. It may be infinite, extending without an edge. It may have a shape so global and strange that local measurements make it look simple, the way a small patch of Earth can look flat while the whole planet curves beneath it. This is where the science becomes quietly astonishing. Cosmologists study the shape of space by looking at the cosmic microwave background, the ancient afterglow of the early universe, and by measuring how matter and light are distributed across enormous scales. If space were strongly curved, triangles drawn across cosmic distances would behave differently from the way they do in flat geometry. Patterns in the oldest light would appear slightly shifted. Distances would not match expectations, but observations show that on the scales we can measure, the universe is extremely close to flat. This does not prove the universe is infinite. A flat universe could be infinite, but it could also be finite in a more subtle way, looping back on itself with a topology too large for us to detect. Still, the near flatness tells us something important. If the universe does curve back on itself, the curve must be very gentle across the region we can see, meaning the whole may be far larger than the observable part. Think of an ant walking across a huge balloon. If the ant can only explore a tiny patch, the surface may feel flat, even though the full shape is curved. We may be like that ant, studying a cosmic patch too small to reveal the full architecture. This is why the phrase, "bigger than we can ever see," is not just poetic. It comes from the difference between local evidence and global reality. Our instruments can measure the portion of the universe that leaves signals inside our horizon. But if the total universe extends beyond that horizon, then no improvement in technology can automatically reveal it. A better telescope can collect fainter light, sharper light, older light, but it cannot collect light that has never arrived and may never arrive. There is a kind of ignorance built into space-time itself. Some regions may be forever outside our causal reach, not because we are too primitive, but because the expansion of the universe prevents their signals from ever entering our observable domain. This is a strange kind of limit. It is not like being unable to see across an ocean because the air is foggy. It is more like standing inside a moving horizon where the ocean itself carries distant ships away faster than their lanterns can ever reach your shore. And yet scientists can still infer that more may exist beyond the visible part. The universe looks remarkably uniform on large scales. The same kinds of physics appear to hold across the observable region. The cosmic microwave background surrounds us from every direction, with a pattern suggesting that our visible patch is not obviously special or centered. If the universe simply stopped just beyond what we see, or if we were somehow near a true edge, we might expect signs of that boundary, distortions, asymmetries, something in the data shouting that our view is privileged. But the cosmos does not look like a stage built around Earth. It looks like a sample of a much larger whole. That does not prove infinity, but it makes a larger than visible universe a natural possibility. This also changes the meaning of distance. The most distant galaxies we observe are not seen as they are now, but as they were when their light began the journey. Some of the regions that emitted the oldest light are now far beyond the distance they were when the light left them. The universe is not a static room where light crosses from one wall to another. It is a growing fabric, and the map changes while the message travels. So the edge of observation is not a place where a spacecraft could arrive and look over the side. It is a limit in the history of information. Everything you know about the cosmos has reached you by messenger: light, gravity, particles, background radiation. If no messenger can arrive from beyond a certain distance, then beyond that distance, the universe may continue in silence, and silence is not absence. This is the emotional difficulty of cosmology. The universe may be filled with realities that are not hidden in the ordinary sense, but permanently unshared. There may be stars whose light will never reach any future human telescope. There may be galaxies already carried beyond the possibility of contact. There may be regions of space that exist as fully as ours does, yet remain outside every story our instruments can tell. The visible universe, then, is not the universe itself. It is the part that has spoken to us, and we should be humble enough not to confuse speech with existence. This humility does not weaken science. It makes science honest. Science does not claim to own the total cosmos. It maps the reachable, tests the measurable, and then asks what the reachable suggests about the unreachable. That is why the universe may be bigger than we can ever see. Because light has a travel time, space expands, horizons form, and the shape of the whole may be far larger than the patch available to observation. You live inside that patch, inside a sphere of ancient signals, surrounded not by a wall but by unanswered continuation. And perhaps that is the softest terror of all. The night sky feels vast already, yet it may be only the nearest paragraph of a book, whose remaining pages can never be opened. Still, the paragraph is real. It contains galaxies, stars, planets, chemistry, memory, and you. And from within this limited window, the universe has done something remarkable. It has become aware not only of what it can see, but of the possibility that reality continues beyond sight, quietly, endlessly, without needing to be witnessed in order to be there. The cosmic horizon, the edge of what we can know. There is a border around you that no wall marks, no telescope can break, and no traveler can ever cross. Not because it is made of matter, but because it is made of missing information. This border is the cosmic horizon, and it is one of the most humbling ideas in all of cosmology. It does not mean the universe ends there. It does not mean galaxies stop existing beyond it. It means there is a limit to what can ever be known from where we are, because knowledge in the universe must travel. Light has to travel. Gravity has to travel. Any signal, any message, any physical influence must cross space at a finite speed. So the sky you see is not simply a view of places. It is a record of what has had enough time to reach us. The cosmic horizon is the edge of that record. It is the boundary between the universe that has spoken to us and the universe that remains silent. This is already stranger than it sounds, because when you look outward in space, you also look backward in time. A nearby star is seen as it was years ago. A distant galaxy is seen as it was millions or billions of years ago. The deeper we look, the younger the universe becomes in our view, until eventually we reach a glowing surface from the ancient cosmos, the cosmic microwave background. This is often described as the oldest light we can see, but even that phrase needs care. It is not light from the first instant of existence. Before that light was released, the universe was too hot and dense for ordinary light to travel freely. Space was filled with charged particles that scattered photons again and again, turning the early universe into a bright fog. Then, as the cosmos expanded and cooled, electrons and nuclei combined into neutral atoms, and light could finally move freely through space. That released light has been traveling ever since, stretched by expansion into microwaves, surrounding us from every direction, like an ancient photograph of the universe when it first became transparent. In that sense, the cosmic microwave background is not a wall at the edge of space. It is a wall in time. It is the moment before which ordinary light cannot show us what happened. To see earlier, scientists must use other messengers, perhaps neutrinos from the young universe, perhaps gravitational waves from even earlier processes, perhaps subtle patterns left behind in the distribution of matter. But each messenger has its own limits. The universe does not hand over its childhood easily. Some layers of the past may be hidden not by distance, but by the nature of physical interaction itself. This is why the cosmic horizon is more than an astronomical fact. It is an epistemological boundary, a limit on knowing. It tells us that science, as powerful as it is, does not operate from a throne outside reality. It operates from inside a location, inside a time, inside a causal bubble. We are not seeing the universe from nowhere, we are seeing it from here. And here matters. Another observer in a galaxy far beyond our reach would have a different horizon, a different sphere of visible history, a different collection of signals arriving at their instruments. Their observable universe would overlap with ours in some regions, but not in all. They might see galaxies we will never see, and miss galaxies that appear in our sky. This means the observable universe is not a single universal object in the absolute sense. It is a perspective-shaped region, centered on the observer, defined by what can reach them. That does not make it subjective fantasy. It is physically real, but it is local. It is the universe as revealed to one position in space-time. And then there is an even deeper horizon, the future cosmic event horizon. Because the expansion of the universe is accelerating, there are distant regions whose light, if emitted today, may never reach us at all. This is not merely about what we have not seen yet. It is about what may remain forever unseeable. As time passes, extremely distant galaxies will drift beyond practical observability, their light stretched, dimmed, and eventually lost to the cosmic future. Future astronomers, living in a much older universe, may see a darker sky than we do. Many galaxies that are visible to us now may disappear beyond the reach of their instruments. The universe will not become smaller, but the accessible universe will become lonelier. This gives our era a strange privilege. We live at a time when the cosmic microwave background is still detectable, when distant galaxies still paint a history of expansion, when enough evidence remains to reconstruct a grand cosmic story. In the far future, some of that evidence may fade. Knowledge itself may have an expiration date, not because minds become weaker, but because the universe carries its clues away. The cosmic horizon therefore teaches a quiet discipline. Do not confuse reality with accessibility. What lies beyond the horizon may be real, but if no signal from it can ever arrive, it cannot become part of our confirmed knowledge. This is a hard truth for a species built on curiosity. We want every mystery to be a locked door, because locked doors imply keys. But some cosmic mysteries may be more like oceans beyond a shoreline that recedes as you walk toward it. You can learn the shape of the waves near you. You can infer the presence of deeper water. You can build theories about what lies farther out. But you may never stand beyond the horizon and look back. And still, this limit does not make the search meaningless. Limits give knowledge its shape. A map is not false because it has edges. It becomes honest when it marks them clearly. The cosmic horizon is the edge written onto our cosmic map. Here is what light has brought us. Here is what physics allows us to infer, and beyond this, caution must walk beside imagination. Perhaps the deepest lesson is that the universe is not obligated to be fully knowable to the beings it produced. It gave us minds large enough to ask about the whole, but not necessarily a position from which the whole can be seen. And there is something strangely beautiful in that. You are alive inside a sphere of arriving messages, surrounded by ancient light, fading signals, and unreachable silence. Everything you know about the cosmos has crossed a distance to reach you. Every image of a galaxy, every measurement of background radiation, every clue about expansion is a message from somewhere else, arriving late but still meaningful. The cosmic horizon is the place where those messages stop, not where reality ends, but where certainty begins to thin. And maybe that is what makes it sacred in the scientific sense. It is the boundary that teaches humility, the edge that reminds us knowledge is not ownership, and the silence beyond it is not emptiness, but the unknown continuing without us. Cosmic inflation and the birth of bubble universes. A bubble universe is not born with a bang in empty space. It begins when a tiny region of reality stops inflating and becomes capable of having a history. That distinction matters, because the phrase birth of a universe can make it sound as if a finished cosmic sphere suddenly appears somewhere outside our own, shining like a new planet in a larger darkness. But in inflationary cosmology, the picture is stranger and less cinematic. Cosmic inflation is the idea that, extremely early in our cosmic past, space expanded at a tremendous rate for a very brief interval. It was not an explosion of matter flying through pre-existing emptiness. It was space itself stretching, smoothing, and enlarging a region that had once been unimaginably small. This helps explain why the universe we observe is so uniform on large scales, why it appears so close to flat, and how tiny early fluctuations could later become the seeds of galaxies. But when scientists explore how inflation might work, they encounter a deeper possibility. The end of inflation may not have happened everywhere at once. In some models, inflation ends locally. A patch of space exits the inflating state, releases its stored energy into particles and radiation, and becomes a hot, expanding universe. Elsewhere, inflation continues. And if inflation continues elsewhere, then more patches can exit later, each one beginning its own cosmic evolution. That is the birth of bubble universes. Not bubbles drifting through the space we know, but regions where inflation has ended inside a larger inflating background. To understand this, think less of soap bubbles floating in air, and more of pockets of ordinary physics forming inside a state that is not yet ordinary. During inflation, space is thought to be dominated by a special energy condition, often described through a field. A field, in physics, is something that has a value everywhere, like a hidden temperature of reality itself. If that field sits in a high-energy state, it can drive rapid expansion. But high-energy states are often unstable or temporary. They may decay, transition, or roll toward a lower energy condition. When that happens in a local region, the energy that once drove inflation can transform into a hot bath of particles. This stage is often called reheating, and it is crucial. Without reheating, an ended inflationary region would not automatically contain the matter and radiation needed for a universe like ours to develop. Reheating is the moment when the abstract energy of inflation becomes the ingredients of cosmic history. It is where a silent stretch of space becomes hot enough to begin forming the conditions that later allow atoms, stars, galaxies, and eventually the chemistry of life. In that sense, a bubble universe is not born complete. It is born as a beginning, as a set of conditions that can unfold. Its galaxies are not present at birth. Its planets are not waiting fully shaped. Its future is encoded in the energy, expansion, fluctuations, and laws active inside it. The bubble begins as a young cosmos with its own clock, its own thermal history, its own path from smoothness to structure. And from the inside, inhabitants billions of years later might not see the bubble wall or the inflating background beyond it. They would see a universe that appears to have begun in a hot, dense state, just as we do. This is one of the most humbling aspects of inflationary thinking. What feels like the beginning of everything from within may be only the local beginning of a region. The birth of a bubble universe could be hidden behind its own history, leaving observers to reconstruct the process from subtle traces rather than direct memory. Tiny quantum fluctuations during inflation are especially important here. Inflation stretches these small irregularities across enormous distances, and after inflation ends, those irregularities become slight differences in density. Over time, gravity amplifies them. Denser regions pull in more matter. Gas gathers, stars ignite, galaxies grow. So the same inflationary process that may create a bubble universe may also plant within it the seeds of its future structure. This is not poetry. It is one of the most powerful ideas in modern cosmology. The largest structures in the universe may have originated from microscopic fluctuations stretched by early expansion. The smooth cosmic background and the clumpy universe of galaxies are not opposites. One grows from the other. The calm field becomes a universe with texture. The nearly featureless beginning becomes a sky full of structure. But the birth of bubble universes remains speculative. We do not have proof that our universe is one bubble among many. We have evidence consistent with inflationary ideas in broad ways, but the details of what powered inflation, whether it occurred exactly as described, and whether it becomes eternal in the larger picture remain open questions. This honesty is essential. Bubble universes are not confirmed worlds. They are possible consequences of certain models. Their beauty should not trick us into certainty. A careful scientist asks, what predictions follow? What traces might inflation leave? What patterns in the cosmic microwave background, galaxy distribution, or primordial gravitational waves could support or challenge these models? A careful storyteller must do the same in another language. Make the wonder sharp, but do not sell the unknown as if it has already been photographed. Still, even as a possibility, this idea changes the meaning of birth. We are used to beginnings as singular events. One start, one origin, one first moment. Inflationary bubble cosmology suggests beginnings might be local transitions. A larger inflating reality may contain many exits from inflation, many reheatings, many hot young regions becoming universes in their own right. Some may be empty of complexity, some may be brief, some may expand forever, some may have conditions unlike ours, and perhaps one of them became this cosmos, with its galaxies, its old light, its dust, its oceans, and its fragile observers. If that is true, then the birth of our universe was not a spark in nothingness, but a phase change in something deeper. A moment when one patch of reality settled into a form where time could gather events and matter could become memory. That thought should be handled softly. It does not erase the Big Bang. It reframes it. The hot early universe remains part of our best cosmic story. Inflation, if correct, describes what may have prepared the stage before that hot history became visible to us. Bubble universes, if they exist, extend the stage beyond our region in a way we may never directly enter. And so the birth of a bubble universe is not only a scientific mechanism, it is a meditation on how the ordinary can emerge from the almost unimaginable. Space stretches, a field changes state, energy becomes particles, fluctuations become galaxies, galaxies become stars, stars become elements, elements become bodies, bodies become listeners, and somewhere along that long unfolding, a universe that began as a local end to inflation becomes capable of asking how it was born. That may be the most astonishing part. Not that bubble universes might exist, but that one small region, after cooling from such ancient violence, could eventually produce minds gentle enough to wonder about the process without claiming to own the answer. Why randomness matters in a huge universe. Randomness is not the opposite of order. In a huge universe, it may be the quiet reason order has anything to grow from at all. When people hear the word random, they often imagine meaninglessness, chaos, a careless roll of cosmic dice with no structure behind it. But in physics, randomness is more subtle than that. It does not mean anything can happen. It means that within the rules, outcomes can vary in ways that are not fully fixed in advance, and those variations can matter enormously when the stage is large enough. The universe is not a place where pure disorder somehow accidentally became galaxies, stars, planets, and minds. It is a place where law and randomness cooperate. Law provides the boundaries. Randomness provides the differences. Without the laws of gravity, matter would not gather. Without the laws of electromagnetism, atoms and chemistry would not behave. But without small irregularities, without tiny unevenness in the early universe, everything might have remained too smooth, too featureless, too perfectly spread out to become anything interesting. A perfectly uniform universe would be strangely sterile. No denser regions, no preferred places for gravity to begin its slow work, no seeds for galaxies, no cosmic web, no long chain from gas clouds to stars, from stars to elements, from elements to planets, from planets to living chemistry. The universe needed imperfections. It needed slight differences from one place to another. And this is where randomness becomes creative, not because it has intention, but because it gives structure something to amplify. In modern cosmology, the tiny temperature differences seen in the cosmic microwave background are connected to early variations in density, and these variations became the seeds from which large-scale structure grew. Gravity took the slightly denser places and made them denser still. Matter fell inward, clouds formed, stars ignited, galaxies assembled. What began as almost nothing, a faint unevenness in an otherwise smooth young cosmos, became the architecture of the visible universe. This should change how you think about chance. Randomness does not have to shout to change history. Sometimes it only has to lean very slightly in one direction. A tiny early difference can be stretched by time into a galaxy. A small fluctuation can become a place where billions of stars form. A minor variation can become the background condition for a planet like Earth to exist billions of years later. And when the universe is huge, even low probability events become important, not because probability guarantees every fantasy, but because vastness gives rare possibilities more room to occur. This is the second lesson. In a small universe, chance may seem like a detail. In a huge universe, chance becomes a population. If you roll a die once, one result appears and the others remain only possibilities. If you roll it trillions upon trillions of times, patterns emerge. You still cannot predict each individual roll with certainty, but you can predict the broad distribution. Randomness, repeated across large numbers, becomes statistical order. The same principle helps science study systems too large or too complex to track particle by particle. A single molecule in a gas may move unpredictably in detail, but a room full of molecules has temperature and pressure. A single mutation may be accidental, but evolution across populations and generations produces adaptation under selection. A single star-forming region may have messy details, but galaxies across the universe reveal large-scale patterns. Randomness at one level can become regularity at another. This is one of the quiet miracles of science. The universe can be unpredictable in the small and understandable in the large. But the opposite is also true. A universe can follow rules and still produce outcomes that feel deeply contingent. Not everything that happens was written like a sentence waiting to be read. Some things emerge from sensitivity, timing, environment, and chance. The particular shape of a galaxy, the exact arrangement of planets in a system, the timing of impacts, the chemical accidents that may lead toward life. These are not always inevitable results of a cosmic plan. They are histories, and histories are shaped by both rules and accidents. This matters for the multiverse because a huge reality changes the emotional weight of randomness. If there are many regions of space, or many cosmic domains, or simply a vast enough universe, then randomness can produce tremendous variety without needing each outcome to be separately designed. Some regions may be dense in galaxies, some may be emptier, some planets may be stable, others may lose their atmospheres, freeze, burn, or never form at all. Some worlds may receive the right sequence of ingredients and calm, others may be interrupted too early by violence or stripped of possibility. Randomness does not make all places equal. It makes each place the result of a particular history, and that particularity is what gives the universe texture. Still, randomness must be respected, not exaggerated. It does not mean that because the universe is huge, anything you can imagine must exist somewhere. Physical laws still limit what can happen. Probability is not magic. A huge universe may allow rare arrangements, but it does not allow contradictions. It may produce variety, but not freedom from physics. This is where many people misunderstand cosmic chance. They turn it into a wish machine. Somewhere, every dream, every story, every impossible world must be real. But science is stricter. Randomness works inside the possible, not outside it. The question is not whether imagination can invent a scenario, but whether the laws of nature allow it, whether there is enough opportunity for it, and whether the probability is meaningful within the size and history of the universe. That is why randomness matters scientifically. It helps explain how complexity can arise without pretending complexity was guaranteed. It gives us a way to understand why the universe is neither perfectly ordered nor completely chaotic. It is patterned but not scripted, structured but not identical everywhere, lawful but not frozen. And this may be the deepest lesson for you as a conscious being inside it. Your existence is not simply the result of one clean cause. It is the meeting point of cosmic regularity and historical accident. The laws of physics allowed atoms, stars forged elements, planets formed from debris. Earth followed one path among many possible planetary histories. Biology emerged through processes that include variation and selection. Your own life unfolded through choices, encounters, timing, inheritance, environment, and countless fragile details. To say randomness matters is not to say your life is meaningless. It is to say your life is not mechanically obvious. You are not the inevitable final line of the universe. You are something more delicate. A rare pattern that became possible because the universe is lawful enough to build structure and open enough for variation to matter. That should not make existence feel empty. It should make it feel astonishing. The same cosmos that could have remained smooth gave birth to unevenness. The same unevenness became galaxies. The same galaxies made stars. The same stars made the elements that became breath, blood, memory, and the quiet ability to wonder about chance itself. So randomness is not just noise in the machinery. It is the small tremor that gives the machinery a history. It is the reason the universe is not a blank sheet, but a page with texture, difference, consequence, and surprise. And maybe that is what a huge universe teaches most gently. Not that everything is random, and not that everything is destined, but that reality lives in the tension between the two. The laws hold the universe together. Randomness lets it become particular. And somewhere inside that particularity, you appeared, not as proof that chance has a purpose, but as evidence that chance, given enough time and the right laws, can become aware of itself. The Level 1 multiverse, distant regions of our own space. The least exotic multiverse may be the most unsettling, because it does not ask you to believe in new dimensions, magic doors, or different laws of physics. It only asks you to take ordinary space seriously beyond the part we can see. This is the Level 1 multiverse, not a collection of separate realities floating outside our cosmos, not quantum branches splitting away from your choices, not bubble universes with unfamiliar constants, but distant regions of the same larger space, governed by the same basic physics, possibly extending far beyond our observable horizon. In this idea, the word multiverse almost becomes misleading because nothing supernatural has been added. The Level 1 multiverse is simply the possibility that what we call our observable universe is only one cosmic neighborhood inside a much larger universe. The laws would be the same. The kinds of particles would be the same. Gravity would work the same way. Light, atoms, stars, and galaxies would follow the same deep rules. What changes from region to region is not the rulebook, but the arrangement. One region may contain a different distribution of galaxies. Another may have formed slightly different clusters. Another may contain empty stretches far larger than ours. And another, if space is vast enough and the possible arrangements repeat, may eventually resemble our own region in ways that feel almost impossible to say out loud. But before that thought becomes too dramatic, it must be understood carefully. Level 1 is not about discovering another universe with a telescope tomorrow. It begins with the simple fact that our view is limited. The observable universe is the region from which light has had enough time to reach us since the early hot stages of cosmic history. That region is enormous, but it is not necessarily everything. If the whole universe continues beyond that horizon, then there are places whose light has not arrived, and may never arrive, not because they are imaginary, but because cosmic distances and expansion prevent contact. From their perspective, if observers existed there, they would have their own observable universe centered on them. Their visible sphere might overlap with ours if they were not too far away, or it might be entirely separate if the distance were great enough. This is the first powerful lesson of Level 1. The observable universe is not a universal object in the same way for everyone. It is a local window. Each observer has a window shaped by their position in space-time. Reality may extend beyond every window, but no single observer gets the whole view. The second lesson is that sameness of laws does not mean sameness of history. Our region contains a specific cosmic pattern. Galaxies arranged in a web, clusters and voids, a microwave background with tiny irregularities, stars that formed in particular places, planets that emerged around particular suns. These details were shaped by early fluctuations, gravitational growth, and long cosmic evolution. Another distant region of the same space could have started with slightly different initial conditions, while still obeying the same physics. That means it could be recognizable in broad form: galaxies, stars, radiation, dark matter, cosmic structure, yet completely different in detail. It might not contain Earth. It might not contain the Milky Way. It might not contain life at all. The Level 1 idea does not promise familiar worlds nearby. It says that if space is sufficiently large, then distant regions may realize many different possible arrangements allowed by the same laws. This is why scientists sometimes connect Level 1 with the idea of a vast, perhaps infinite universe produced by inflation. Inflation can stretch space so enormously that our observable region becomes only a tiny patch of a much larger whole. If that larger whole is infinite or simply vast beyond comprehension, then the number of horizon-sized regions may be enormous. Each region becomes like a separate cosmic sample, the same underlying physics, but different outcomes. This is not the same as saying everything you imagine exists. Physical laws still rule. The possible is not unlimited fantasy. But within those laws, there are many ways matter and radiation can be arranged, and a vast enough space gives those arrangements room to appear. The Level 1 multiverse is therefore less like a fantasy library of magical worlds and more like an endless landscape of cosmic neighborhoods, all made from the same ingredients, all shaped by the same fundamental grammar, but each with its own sentence written across space. What makes this idea so strange is that it turns distance into a form of separation almost as powerful as difference. A distant Level 1 region would not be another universe in the sense of having different physics, but if it lies beyond our horizon forever, it becomes unreachable in practice. It may be part of the same total space and still remain outside all possible conversation with us. That is a difficult category for the human mind. Real, but inaccessible. Continuous with our cosmos, but forever absent from our evidence except through general reasoning about the whole. We are used to thinking that if something belongs to our universe, then enough patience and technology might one day reveal it. Level 1 teaches that this is not always true. Some parts of the same universe may be permanently hidden by the structure of space-time itself. This does not make them less real if the larger model is correct, but it does make them scientifically delicate. We cannot catalogue those regions. We cannot map their galaxies. We cannot prove their individual histories. We infer their possibility from cosmological models, from the observed flatness and uniformity of our region, from the success and open questions of inflationary thinking, and from the idea that our visible patch may not be special. The humility here is important. Level 1 is often described as the least speculative kind of multiverse because it does not require new kinds of reality beyond extended space. But least speculative does not mean fully proven in every detail. We still do not know whether the total universe is infinite. We still do not know its global shape. We still do not know how far space continues beyond what we can observe. The Level 1 multiverse is a plausible extension of ordinary cosmology, not a photograph of the unseen. And yet, it quietly changes the meaning of where you are. You may not be living in the central universe, but in one observable patch among perhaps countless patches. The galaxies we see may not be the complete inventory of existence, but only the nearby evidence available to us. The cosmic horizon may not be a boundary around reality, but a boundary around our information. And beyond it, if Level 1 is right, there may be more of the same universe continuing in silence. Not stranger, because its laws are different, but stranger because it is ordinary and unreachable at the same time. That may be the deepest emotional twist. The Level 1 multiverse does not shock you with fantasy, it shocks you with scale. It says, the unknown beyond our horizon may not be a magical elsewhere, but more space, more matter, more history, more regions where the same laws keep unfolding without ever needing to be witnessed by us. And perhaps that is enough to make the familiar universe feel new again. You are not trapped in a small cosmos. You are living inside a visible island of a possible vastness, surrounded by distances so great that even sameness becomes mysterious. The Level 1 multiverse is the thought that reality may continue beyond sight, not as a different dream, but as the same dream, stretching farther than any eye can follow. Wormholes, portals, and the problem of reality hopping. A portal is seductive because it turns the impossible into architecture. One step here, another sky there, and suddenly reality feels like a hallway with hidden doors. But physics is not so generous. The idea of reality hopping, jumping from this universe into another, or from this history into a different one, sounds simple only because stories hide the hardest parts. They show the doorway, the glow, the crossing, the shock of arrival. They rarely show the question underneath. What would it mean for two realities to be connected at all? A wormhole in serious physics is not a magical door nailed into space. It is a hypothetical geometry of space-time, a possible shortcut where two distant regions are connected through a tunnel-like structure. In the most basic imagination, instead of traveling across the long surface of the universe, you pass through a deeper fold and emerge somewhere else. But even that picture is only a metaphor, because space-time is not a sheet you can simply bend with your hands, and the universe does not provide shortcuts just because distance is inconvenient. General relativity, Einstein's theory of gravity, allows strange shapes of space-time in its equations, and some of those shapes resemble bridges. The famous Einstein-Rosen bridge is one early example, but it is not the friendly portal of fiction. In its ordinary form, it would collapse too quickly or be impossible to cross in any useful way. Later ideas about traversable wormholes are more carefully designed, but they bring a severe price. To keep a wormhole open, many models require exotic matter or negative energy conditions, something that behaves unlike ordinary matter. Ordinary matter pulls, weighs, curves, and collapses in familiar ways. A traversable wormhole would need space-time to be held open against its natural tendency to pinch shut. That is not a small engineering challenge. It is a deep physical problem. We have seen tiny quantum effects that can produce forms of negative energy in limited contexts, but nothing close to the controlled, stable, massive structure that would let a human being step through a cosmic tunnel. So the first honest truth is this: wormholes are mathematically interesting, not practically available. They are tools for testing what relativity might allow at the edges, not evidence that portals are waiting in the dark. And even if a traversable wormhole existed, the problem of reality hopping would not be solved. A wormhole connecting two places in the same universe is already difficult enough. A wormhole connecting different universes is far more speculative. It assumes the two realities share some deeper structure through which a bridge can exist. But if another universe is truly separate, causally disconnected, governed by different conditions, or existing as a quantum branch that no longer interacts with ours, then travel may not be the right word. Travel assumes continuity. It assumes your body can move through a path while remaining itself. It assumes the destination shares enough physics to receive you. Another universe may not grant those assumptions. If its laws differ, your atoms might not be stable there. If its time behaves differently, your sense of sequence might fail. If it belongs to a quantum branch, there may be no spatial direction leading to it. You cannot walk north into an alternative measurement outcome. You cannot build a door into a history that has decohered away from yours. The word portal makes reality sound local, as if every possible world is just behind a thin curtain. Physics suggests something more difficult. Separation can be structural, not spatial. Two branches can be separated without being far away. Two cosmic regions can be unreachable without a wall between them. Two universes can be mathematically imagined without sharing any corridor. This is why reality hopping is such a dangerous phrase. It compresses several different ideas into one exciting image. There is interstellar travel, which means moving through our own space. There is time travel, which would mean moving through the causal structure of events. There is quantum branching, which describes different outcomes in some interpretations of physics. There are bubble universes, which may be separate regions born from inflationary processes. There are hidden dimensions, which may exist in some high-energy theories, but are not confirmed as navigable spaces. Calling all of these portals makes them feel similar, but they are radically different problems. A shortcut across our universe is not the same as entering a different universe. Entering the future by time dilation is not the same as rewriting the past. Imagining a quantum branch is not the same as visiting it. The universe does not become easier to cross just because language gives every mystery the same door shape. And then comes the deeper issue of causality. A traversable wormhole, if one mouth were moved or placed in a different gravitational environment, could in some theoretical setups behave like a time machine, allowing closed loops in time. That sounds thrilling, but to physics it is a warning sign. Closed causal loops threaten paradox, information with no origin, effects before causes, histories that undermine themselves. Some physicists suspect that nature may protect causality in ways we do not yet understand, preventing such time machines from forming or remaining stable. This is not proven in a final sense, but it shows why portals are not just transportation devices. They are attacks on the order by which events make sense. A real portal would not merely shorten distance. It might challenge identity, conservation, chronology, and the stability of space-time itself. If you stepped through and emerged in another reality, what exactly crossed? The atoms of your body? The information pattern that describes you? Your memories? Your conscious viewpoint? If the portal copied you instead of moving you, would the person arriving be you or a continuation that only believes it is you? Fiction usually avoids this because it wants adventure. Science cannot avoid it because the question of transfer is physical. A body is not a symbol. It is matter arranged with extreme precision. Moving it across a space-time shortcut would require preserving that arrangement through intense gravitational conditions, radiation, tidal stress, and perhaps unknown quantum effects. Hopping between realities would require even more compatibility between the origin, the bridge, and the destination. Without that compatibility, a portal is not a doorway. It is a shredder with a beautiful frame. Still, the reason wormholes remain fascinating is not that they promise escape, but that they reveal how flexible our concept of space became after relativity. Before Einstein, space felt like a fixed stage. After Einstein, space and time became dynamic, curved by energy and matter, capable in principle of shapes far stranger than everyday intuition allows. Wormholes live in that freedom. They show that the equations of gravity are not limited to the gentle geometry of rooms, roads, and orbits. They allow us to ask how far space-time can be bent before reality refuses. They act like thought experiments with teeth. They do not say, "Here is a portal." They ask, what would the universe have to be like for a portal to exist? And every answer teaches us something. It teaches us about energy conditions, quantum limits, horizons, causality, and the difference between mathematical permission and physical existence. That difference may be the central lesson. A shape can exist in equations without existing in nature. A solution can be allowed in a simplified model and still be unstable, unbuildable, or forbidden once the full rules are included. The world is not required to instantiate every elegant possibility. This is where mature wonder begins. Not in believing the portal is waiting, but in understanding why the portal is so hard to make real. So could we ever hop between realities? With current science, there is no known method, no evidence of natural portals, and no tested path to another universe. Wormholes remain hypothetical. Traversable wormholes remain deeply speculative. Inter-universe travel is even more uncertain. But the question is not useless. It teaches you that reality is not a hallway, and mystery is not automatically a door. Some boundaries may be crossed by technology, others may be built into the structure of existence. And perhaps the most honest ending is also the most humbling. The universe may contain shortcuts in its mathematics that nature never opens for travelers. Yet by studying those impossible doors, we learn the shape of the walls around us. And sometimes that is the closest thing to crossing them. Hidden dimensions and other realities. The strangest rooms in reality may not be far away at all. They may be folded so closely into the space around you that every breath passes beside them without ever entering. Hidden dimensions are often misunderstood because the word dimension sounds like another universe, another realm, another glowing layer of existence waiting just beyond sight. But in physics, a dimension is first a direction of freedom, a way something can vary or move. You know 3 large dimensions of space because your body lives through them constantly, left and right, forward and back, up and down. Time adds another kind of ordering, the sequence through which events unfold. These dimensions feel obvious because they are large enough for you to move through and stable enough for your senses to build a world from them. But some theories ask whether these familiar directions are the whole story. What if space has additional dimensions that are real, but hidden because they are curled up at scales far too small to notice? The classic way to picture this is with a thin cable seen from far away. From a distance, it looks like a one-dimensional line stretching across space. But an ant crawling on it can move not only along its length, but also around its tiny circular thickness. The extra direction was there all along, but it was too small for a distant observer to resolve. In a similar spirit, extra-spatial dimensions might exist not as vast open territories, but as tiny compact shapes woven into every point of space. You do not see them because you are enormous compared with them, and because the particles and forces you are made of may not have access to them in ordinary ways. This idea is not fantasy invented to make the universe feel mysterious. It has appeared in serious attempts to unify physics. In the early 20th century, Kaluza and Klein explored whether adding an extra dimension could link gravity and electromagnetism in one geometric framework. Later, string theory suggested that the basic ingredients of matter may not be point-like particles, but tiny vibrating strings, and the mathematics of such theories often requires more dimensions than the 4 we experience directly. In that view, the hidden dimensions are not optional decoration. They help determine how strings vibrate, and those vibration patterns could appear to us as different particles and forces. The shape of the hidden dimensions would matter deeply, like the shape of a musical instrument shaping the sound it can produce. A violin string and a guitar string both vibrate, but the body around them changes the voice. In some versions of string theory, the extra dimensions form intricate compact geometries, too small to see but powerful enough in principle to influence the physics we observe. This is where the idea becomes quietly profound. Reality may have a hidden shape that does not look like landscape, sky, or distance, but still affects why the visible world behaves as it does. The particles in your body, the strength of forces, the way matter holds together, may be connected to geometry you cannot picture. But caution is essential. Extra dimensions have not been proven. No experiment has confirmed that hidden spatial directions exist. They remain theoretical possibilities, explored because they may help solve deep problems, not because scientists have already found them. If they exist, how could we know? One possibility is through particle physics. Extra dimensions could reveal themselves by creating heavier versions of known particles, sometimes called Kaluza-Klein excitations, because movement in a hidden dimension could appear to us as extra mass or energy. Another possibility involves gravity. Gravity is much weaker than the other forces, and some models suggest this weakness could be related to gravity spreading into extra dimensions, while other forces remain confined to the familiar ones. If that were true, high-energy experiments might show missing energy, unusual particle behavior, or even speculative signatures such as microscopic black holes under extreme conditions. This is why facilities like the Large Hadron Collider have searched for signs of extra dimensions, not by opening portals, but by looking for deviations from known physics. So far, no confirmed signal has appeared. That absence is meaningful. It does not disprove every possible extra-dimensional model, but it does constrain them. It tells scientists that if hidden dimensions exist, they are not revealing themselves easily at the energies and scales we have tested. This is how real science handles wonder. It lets the idea breathe, but it also tightens the net of evidence. Hidden dimensions also raise a deeper question about perception. If they exist everywhere, why do we experience only 3 dimensions of space? The answer may be practical rather than philosophical. Our bodies, brains, and instruments evolved and operate inside the large dimensions. We are built from particles whose behavior gives rise to stable atoms, chemistry, surfaces, motion, and distance as we know them. If extra dimensions are compact and tiny, then ordinary objects cannot simply turn into them any more than a train can drive around the microscopic circular surface of its own rail. The hidden direction may be real, but inaccessible to macroscopic life. This makes hidden dimensions different from the popular idea of other realities as places you can visit. They may not be places at all in the everyday sense. They may be part of the local structure of space, present at every point, shaping physics from beneath visibility. The word other realities becomes more subtle here. It does not necessarily mean a separate world with mountains, oceans, and alternate histories. It could mean that the reality you already inhabit has layers your senses cannot unfold. The visible universe may be like a sentence written on the surface of a page, while the hidden dimensions are the grain of the paper itself, influencing how the ink can settle without becoming part of the sentence you read directly. And perhaps that is more unsettling than a distant realm, because it means the unknown is not only beyond the stars. It may be beneath scale, beneath perception, beneath the smooth feeling of ordinary space. Still, we must not confuse mathematical possibility with confirmed existence. Hidden dimensions are a serious idea because they arise in serious theories and because they can, in some models, produce testable consequences. But they remain unverified. They are not evidence that ghosts, spiritual planes, or fictional portals are real. They are not a license to call every mystery a dimension. In science, a hidden dimension must do work. It must help explain physical behavior, fit into a coherent theory, and ideally leave traces that experiments can seek. Without that, the word becomes only decoration. But when handled carefully, the idea opens a breathtaking possibility. The world may be simpler to experience than it is to be. Your senses give you a clean stage because life needs a usable interface. You reach, walk, turn, remember, and your brain builds a world of stable directions. Yet underneath that usable world, space may have a deeper architecture, curled, compact, and silent, shaping the laws without ever becoming visible as a road. If hidden dimensions exist, they would not make your reality fake. They would make it partial. They would show that what feels like all of space is only the large, open part of a richer structure. And if they do not exist, the search still teaches us something valuable. That science is willing to question even the most basic assumptions, including the number of directions reality has. So tonight, the room around you may feel simple. A floor, a ceiling, 4 walls, a body resting in 3-dimensional space. But physics whispers that simplicity may be an achievement of perception, not the final shape of existence. There may be hidden geometry folded into every point, or there may not. The truth remains unfinished, yet the question itself changes the ordinary room. It makes space feel less like emptiness and more like a surface above depths, where the most important directions may be the ones you cannot move through, cannot see, and cannot imagine, yet may still be part of the quiet structure holding you here. Brain worlds, universes like sheets in higher dimensions. What if everything you call the universe is not the whole room, but only a thin surface inside a much deeper space you cannot step into? This is the strange promise of brain world cosmology. The possibility that our entire visible reality, every galaxy, every star, every atom in your body, every beam of light that has ever reached a telescope, could be confined to something like a cosmic sheet embedded in higher dimensions. The word brain comes from membrane, but you should not picture a rubber sheet floating in a dark warehouse, because that image becomes misleading if held too literally. A brain is not necessarily a physical cloth with edges you could touch. It is a lower dimensional surface or region inside a larger dimensional space, often called the bulk. In some brain world models, our universe is a 3-dimensional brain, meaning that the familiar space we move through may be like a surface within a higher dimensional reality. You can walk left and right, forward and backward, up and down, but there may be directions beyond those that ordinary matter cannot access. The reason this idea became serious is not because it sounds dramatic, But because certain theories connected to string theory and M theory naturally include extended objects like branes, and some models use them to rethink one of the deepest puzzles in physics: why gravity seems so weak compared with the other forces. In everyday life, gravity feels powerful because it holds planets, stars, and galaxies together. But at the scale of particles, gravity is astonishingly weak. A tiny magnet can lift a paperclip against the gravitational pull of the entire Earth. This imbalance is known as part of the hierarchy problem, and Brane world models offer one possible way to think about it. Maybe gravity is not truly weak. Maybe it only appears weak to us because it can spread into the higher dimensional bulk, while the particles and forces that make up ordinary matter are mostly trapped on our brain. If light, electrons, atoms, and chemistry are confined to the brain, then your senses would naturally report the brain as the whole universe. You would not see the bulk, because the light you used to see would be stuck with you. You would not reach into the extra dimension, because your body is made from fields that do not freely move that way. Gravity, however, might leak or extend into the bulk, and that leakage could make it appear diluted from our perspective. In some versions, the extra dimension is not simply large and open, but warped, meaning the geometry itself changes how gravity behaves. The Randall-Sundrum models are famous examples of this. They suggest that the shape of the higher dimensional space could help explain why gravity seems so weak without requiring all extra dimensions to be tiny in the usual way. This is a powerful lesson because it turns weakness into perspective. What looks like a small force from inside the brain might be the shadow of a larger geometry outside ordinary perception. But the idea becomes even stranger when you ask whether there could be other branes. If our universe is one brane in a higher dimensional bulk, then perhaps another brane could exist elsewhere in that bulk, separated from us not by ordinary space, but by a direction we cannot move through. It might be close in a higher dimensional sense and still completely invisible. It could contain its own matter, its own structures, perhaps its own cosmic history, while remaining dark to us because our light and particles cannot cross the gap. This is where Brane worlds begin to sound like parallel realities. But the careful difference matters. A neighboring brane would not necessarily be another version of Earth, another timeline, or a mirror copy of your life. It would be a separate physical surface or region in a higher dimensional framework. It might have different fields living on it. It might interact with ours only through gravity, or not in any measurable way at all. If such a brane existed, it would not glow in the night sky. It would not appear as a hidden planet. It would be absent from our senses, because the rules governing ordinary particles could keep the two worlds separated more completely than any war. This is the unsettling beauty of the Brane world idea. Separation does not always require distance in the directions you know. Two realities might be divided by a dimension your body cannot enter. A page in a book can sit next to another page, but a character drawn on one page cannot simply walk onto the other unless the ink itself is allowed to leave the surface. In the same way, if we are brane-bound beings, then the bulk may surround us without becoming available to us. Some Brane world cosmologies even explore whether a collision between branes could have played a role in cosmic beginnings. In certain speculative models, what we interpret as a hot early universe might be connected to the interaction or approach of branes in higher dimensional space. This is not established fact, and it should not be presented as a replacement for the standard Big Bang model. It is an attempt to ask whether the beginning we infer from our cosmic history might have a deeper geometric cause. The idea is bold. Perhaps cosmic fire could come not only from expansion from an early hot state, but from dynamics between higher dimensional surfaces. But boldness is not proof. Brane cosmology remains speculative. No experiment has confirmed that we live on a brane. No detector has found clear evidence of large extra dimensions. No collider has produced unmistakable signs that gravity is escaping into a bulk. Scientists have searched for possible clues, such as deviations from familiar gravity at very small distances, missing energy in particle collisions, unusual gravitational behavior, or cosmological signatures that would not appear in ordinary four-dimensional models. So far, the evidence has not forced us into a brain world picture. That matters. A beautiful model does not become reality just because it explains a puzzle elegantly. Physics must answer to the world. And yet, even unconfirmed, brain worlds teach a profound concept. Our universe may be an effective reality, not necessarily the full arena. Effective does not mean fake. It means that the laws we experience may be the laws available on our brain, just as waves on the surface of water follow surface rules, even though the ocean has depth below. If you lived as a ripple, the surface would be your cosmos. Depth would be real, but not part of your ordinary motion. This idea reshapes the meaning of confinement. You do not feel trapped in 3 dimensions because they are enough for daily life. A room, a road, a body, a sky, everything seems complete. But completeness may be a feature of perception, not the final structure of reality. If brain world models are right, then the most important boundary around us is not at the edge of the observable universe. It is everywhere, at every point, in the fact that ordinary matter may be tied to a surface it cannot leave. The prison, if it is a prison, has no visible bars, because the bars are the rules of matter itself. Still, there is a quiet comfort hidden here. If we live on a brain, then our world is not diminished. It is made more intricate. The stars are still stars. The earth is still real. Your thoughts still unfold inside a body held together by local physics. A deeper bulk would not erase the familiar. It would give the familiar a hidden context. It would mean that reality has layers, and that the layer we call home is stable enough to hold galaxies, chemistry, memory, and wonder. Maybe there are other brains beyond our reach. Maybe there are not. Maybe the bulk is only a mathematical possibility. Or maybe it is part of the architecture we have not yet learned to test. For now, brain worlds remain at the edge of known physics, serious enough to study, uncertain enough to doubt, beautiful enough to disturb the simplicity of space. And perhaps that is the softest lesson they leave behind. You do not have to travel to another universe to discover that reality may be deeper than it looks. You may already be living on a surface, surrounded by dimensions you cannot enter, held in place not by walls, but by the quiet loyalty of the laws that make you possible. The string theory landscape. The string theory landscape is what happens when a theory searching for one final answer opens its eyes and finds a wilderness of possible answers instead. For a long time, the dream of fundamental physics was beautifully simple. Beneath every particle, every force, every constant, there might be one deep structure so elegant that the universe could not have been otherwise. String theory seemed to offer something like that dream. Instead of treating particles as tiny points with no inner shape, it imagined that the most basic ingredients of reality might be unimaginably small vibrating strings, and that different patterns of vibration could appear to us as different particles. It also promised, at least in spirit, a way to bring gravity and quantum mechanics into the same framework, 2 pillars of physics that do not easily fit together. But as the theory developed, something unexpected happened. The search for one unique universe did not lead to one unique solution. It led to many. Not many in the sense of a few alternative designs, but a vast landscape of possible vacuum states. Possible ways the hidden geometry of extra dimensions could be shaped. Possible ways fields and fluxes could settle. Possible low-energy worlds that might each have different particles, forces, constants, and cosmic behavior. This is what physicists call the string theory landscape. Not a place in space, not a valley you can travel through, but a conceptual terrain of possible universes allowed by the mathematics of string theory. To understand why this matters, you have to understand the word vacuum in a deeper way. In everyday language, a vacuum means empty space. But in modern physics, the vacuum is not simple nothingness. It is the ground state of fields, the background condition that determines what kinds of particles can exist, how forces behave, and what the apparent laws of physics look like to observers inside that state. If string theory allows many different vacua, then it may allow many different versions of ordinary physics at large scales. One vacuum might produce a universe with something like our particles. Another might produce a universe with different particle masses, different force strengths, a different amount of vacuum energy, or no stable matter in the familiar sense. The landscape idea says that the deep theory may be one, but its possible settled states may be numerous. This is like one instrument capable of producing many notes depending on how it is tuned, except the instrument is the underlying structure of reality, and the notes are entire physical worlds. The hidden extra dimensions are central to this picture. String theory typically requires more dimensions than the three large spatial directions we experience, and those extra dimensions are thought to be compactified, curled into shapes too small for ordinary perception. But their shape is not a minor detail. The geometry of those hidden dimensions can influence the physics that appears in the large dimensions. Change the hidden shape, and the visible universe may change with it. Add different arrangements of flux, field-like quantities threading through the compact dimensions, and the possible outcomes multiply. The result is not a single road leading from string theory to our universe, but an immense terrain of possible low-energy realities. This is why the landscape is both exciting and troubling. It is exciting because it offers a way to think about why our universe has the properties it has. Perhaps the constants and particles we observe are not the only possible result of fundamental theory. Perhaps they are the local features of one vacuum among many. But it is troubling because if a theory allows too many possible universes, it becomes harder to predict why ours should be this one. A theory that predicts one result can be tested sharply. A theory that allows countless results risks becoming flexible enough to fit almost anything. This is the core criticism of the landscape. Does it explain our universe? Or does it weaken explanation by saying there are so many possibilities that ours is simply one of them? That question is not a small objection. It is one of the deepest debates surrounding string theory. Some physicists see the landscape as a failure of uniqueness, a sign that the theory may not deliver the clean predictive power once hoped for. Others see it as a discovery about reality's structure, suggesting that diversity of physical laws may be unavoidable in a deeper theory. The cosmological constant problem made the landscape especially important. Our universe appears to have a very small but non-zero dark energy-like effect, driving accelerated expansion. In many theories, vacuum energy could have been enormously larger, which would have prevented galaxies and stars from forming in the way they did. The string landscape, especially when combined with anthropic reasoning, offers one possible explanation. If there are many vacua with many possible values of vacuum energy, then observers naturally find themselves in one of the rare vacua where the value allows galaxies, stars, and long-lived complexity. This does not prove the landscape is real. It does not prove the multiverse. It does not prove that anthropic reasoning is the final answer, but it shows why the idea entered serious physics. It tried to connect a difficult observed feature of our universe with a vast range of possible theoretical states. Still, this solution comes with a cost. If you explain why the universe is life-permitting by saying many different vacua exist, and we occupy one compatible with observers, then you must also explain how those vacua are realized physically. Are they merely mathematical possibilities, or do they actually exist as different cosmic regions? Eternal inflation is often brought into the story here because it may provide a mechanism for different regions of a larger reality to settle into different vacua. In that picture, the landscape becomes more than a menu of possible laws. It becomes a cosmic environment where different entries on the menu may be instantiated. But this combined picture is speculative. It depends on pieces that remain unconfirmed. The exact truth of string theory, the reality of the landscape, the mechanism of vacuum selection, the details of inflation, and the way probabilities should be counted across a multiverse. The measure problem returns here with force. If there are enormous numbers of possible vacua, and perhaps enormous numbers of regions realizing them, how do you decide what a typical observer should see? How do you make predictions rather than simply telling stories after the fact? A landscape without a reliable map can become fog, and yet, even fog has shape when enough careful minds move through it. The string theory landscape teaches something profound about the difference between elegance and reality. Human beings love the idea that the deepest truth must be simple in the way we find beautiful. One equation, one answer, one unavoidable cosmos. But nature has never promised to satisfy that aesthetic. It may be that the fundamental framework is elegant, while its possible outcomes are wildly diverse. Or it may be that the landscape is a warning sign, telling us that we have not yet found the right formulation. Some newer ideas, often grouped under the swampland program, ask whether many apparent solutions in the landscape are actually inconsistent when quantum gravity is taken seriously. In other words, not every mathematical-looking low-energy universe may belong to the true landscape. Some may sit in a surrounding swamp of possibilities that cannot really exist. This attempt to separate consistent worlds from inconsistent ones is part of the ongoing struggle to regain predictive power. It shows that the landscape is not a finished doctrine. It is a battlefield of interpretation, calculation, and doubt. That is exactly why it is worth teaching honestly. The string theory landscape is not a proven catalogue of real universes. It is not a secret atlas of places beyond our sky. It is a theoretical possibility arising from attempts to understand how string theory might produce the physics we observe. Its importance lies not only in whether it turns out to be true, but in how it transforms the question. Instead of asking only, why do the laws have these values? It asks, could the laws we see be environmental outcomes within a deeper theory? Instead of assuming the universe must be unique, it asks whether uniqueness is a human hope rather than a physical requirement. And this can feel destabilizing. If our universe is one vacuum among many, then the laws that feel ultimate from within may be local features of a deeper terrain. Gravity, particles, dark energy, chemistry, even the possibility of stars. These may depend on where reality settled in the landscape. But that does not make this world less real. A valley is not unreal because mountains surround it. A note is not unreal because the instrument can play others. If the landscape exists, then our universe is the valley in which matter found enough stability to become stars, planets, bodies, and thought. You are not living in the whole terrain. You are living inside one settled possibility, one physical climate, one rare arrangement where the rules allow memory to form and ask where the rules came from. Maybe the landscape is real. Maybe it will be narrowed, reshaped, or replaced by a deeper theory. Maybe the dream of one unique answer will return in a form we cannot yet imagine. But for now, the string theory landscape leaves us with one of the strangest lessons in modern physics. The final theory, if it exists, may not point to one universe like an arrow, looking for multiverse clues in the cosmic microwave background. The oldest light in the universe may look calm at first, but cosmologists study it the way detectives study a silent room after something enormous has already happened. This light is the cosmic microwave background, often called the CMB, and it is not ordinary starlight, not a glow from galaxies, not a signal from one direction in the sky. It is radiation coming from everywhere, a cooled remnant of the early universe, released when the cosmos became transparent enough for light to travel freely. Before that moment, the universe was like a dense, glowing fog, filled with charged particles that kept scattering photons again and again. Light existed, but it could not move far without being interrupted. Then, about 380,000 years after the hot early phase, the universe cooled enough for electrons and nuclei to combine into neutral atoms, and suddenly, light could stream across space. That light has been traveling ever since, stretched by the expansion of the universe until it now appears as microwaves. When satellites like COBE, WMAP, and Planck mapped it, they did not find a perfectly blank glow. They found a nearly uniform background, but with tiny temperature differences, slight warm and cool patches, subtle irregularities that became one of the most important scientific clues we possess. Those tiny variations are not random decoration. They are the early fingerprints of structure, the seeds that later helped matter gather into galaxies and clusters. So when scientists look for multiverse clues in the CMB, they are not looking for a picture of another universe. They are looking for scars, asymmetries, unusual patterns, or statistical hints that might suggest our early cosmic region was influenced by something beyond the simplest model. That distinction matters. The CMB is not a portal. It is not a cosmic photograph of other worlds. It is more like an ancient surface of last contact, the earliest visible layer of our universe, carrying information about what happened before stars existed. If another bubble universe had collided with ours in certain eternal inflation models, the collision might have disturbed the pattern of that early light. The predicted signal would not be a face, a symbol, or a message. It might appear as a circular or disc-like region with a slightly unusual temperature pattern, perhaps accompanied by a polarization signature. It would be faint, statistical, and difficult to separate from chance, foreground contamination, and ordinary cosmic variation. This is why the search is so delicate. The universe gives us one sky. We cannot rerun cosmic history thousands of times to see what patterns appear by accident. We have to compare the sky we observe against models of what a typical sky should look like if the standard cosmological picture is correct. And the standard picture already explains the CMB extremely well. A hot early universe. Tiny primordial fluctuations, expansion, gravity, dark matter, ordinary matter, and dark energy together produce a remarkably successful account of the large-scale patterns we observe. Any multiverse clue must therefore be more than strange. It must be strange in the right way, and strange enough to survive careful statistical testing. One of the most famous puzzles is the CMB cold spot, a region that appears cooler than expected over a large area of the sky. It has inspired many explanations. A statistical fluke, the effect of a giant cosmic void along the line of sight, unusual early universe physics, or more speculatively, a possible trace of contact with another bubble universe. The last option is the most dramatic, but drama is not evidence. A cold region in the CMB does not automatically mean another universe brushed against ours. The sky contains fluctuations, and rare patterns can appear even in a universe governed by ordinary physics. Large-scale structure between us and the CMB can also affect the radiation slightly as it passes through gravitational landscapes. Researchers have studied whether a supervoid could explain the cold spot, and the debate remains complex, but no explanation has been accepted as definitive proof of a multiverse. This is the honest tension. Anomalies are interesting because they might be clues, but they are also dangerous because the human mind loves to promote a mystery into a revelation before the data is ready. The CMB has other large-scale oddities too, sometimes described as anomalies in isotropy or statistical behavior. Some features appear less random or less evenly distributed than simple models might suggest. The Planck mission confirmed that some of these puzzling features remain present in the temperature data, but later analyses have not transformed them into clear evidence for new physics or other universes. That is important. An anomaly is not the same as a discovery. It is a question mark, and question marks are valuable only if we do not pretend they are answers. Scientists must ask whether an unusual pattern comes from cosmic history, instrument noise, foreground emission from our own galaxy, limitations in data processing, or simply the fact that even random skies sometimes contain surprising features. This is one reason polarization matters. Temperature maps show tiny differences in heat across the ancient light, but polarization tells us about the orientation of that light, shaped by scattering in the early universe. A real primordial feature, such as a bubble collision signal, might leave a related pattern in polarization, giving scientists a second kind of evidence to compare against temperature alone. But polarization is harder to measure with high precision, and the expected signals can be extremely weak. Even future improvements may not guarantee a final answer, because some possible multiverse signatures may be too faint, too rare, or too easily confused with other effects. This is where the CMB becomes a lesson in the limits of cosmic archaeology. Archaeologists on Earth can dig deeper, compare sites, date materials, and sometimes find a clear artifact. Cosmologists have the entire sky, but only one observable universe. They read patterns in radiation that has traveled for billions of years through foregrounds, noise, and gravitational distortions. The evidence is real, but the interpretation demands patience. Looking for multiverse clues in the CMB is not about proving every wild idea. It is about asking whether a speculative theory makes a specific observational prediction and then letting the sky test it as harshly as possible. This is why the search is scientifically meaningful, even without a dramatic discovery. It turns the multiverse from a word into a question with conditions. What would another universe have to do to leave a trace here? What shape would that trace have? How likely is it to arise by chance? Does the data prefer it over simpler explanations? Can polarization confirm it? Can independent analyses reproduce it? If the answer is no, the idea must become weaker. If the answer is yes, then the door opens slightly, but still carefully, because extraordinary claims must survive extraordinary scrutiny. So far, the CMB has not given us a confirmed multiverse signature. It has given us something subtler, a precise map of the early universe, a strong foundation for modern cosmology, and a handful of puzzles that keep theorists alert. Perhaps those puzzles will one day point to new physics. Perhaps they will fade as statistical accidents or foreground effects. Perhaps one faint feature in the ancient light truly is the bruise of another cosmic region, but we do not yet know how to prove it. The honest beauty lies in that uncertainty. The CMB is the oldest visible witness we have, and like all ancient witnesses, it speaks softly, indirectly, and with gaps. We listen by measuring temperature differences smaller than a breath, by mapping polarization across the sky, by building models, and then trying to break them. If the multiverse has touched our universe, the CMB may be one of the few places where that touch could remain. But until the evidence becomes clear, the ancient light asks us not to believe too quickly. It asks us to look carefully, to separate scars from shadows, to let mystery stay mysterious until it earns a name. And as you imagine that faint microwave glow surrounding all of space, remember what it really is. Not proof of other universes, but the oldest readable surface of this one, carrying in its tiny variations the memory of a time before stars, before planets, before eyes, and perhaps, hidden somewhere within its quiet pattern, the first whisper of whether our universe was ever truly alone, why the multiverse might stay forever beyond us. The multiverse may stay beyond us, not because it is hiding, but because reality may have built some of its rooms without doors. That is the hardest part to accept. Human beings are trained by experience to believe that every unknown is temporary. A distant island can be reached by ship. A hidden planet can be found by telescope. A faint particle can be revealed by a better detector. The history of science encourages this hope, because again and again, things once invisible became measurable. Bacteria, atoms, exoplanets, gravitational waves, the afterglow of the early universe. So when we hear about other universes, the instinct is to ask what instrument will finally reveal them? What telescope will see them? What machine will open the path? What signal will prove they are there? But the multiverse may be a different kind of unknown. It may not be hidden in the ordinary sense. It may be separated from us by the structure of causality itself. To know something scientifically, some kind of influence must reach us. Light, gravity, particles, radiation, a distortion in a pattern, a prediction that connects the unseen to the seen. But if another universe has no causal contact with ours, if no signal can travel from there to here, if no event there can leave a trace here, if no shared surface carries information between the two, then it may be real and still remain outside our knowledge forever. That is not a failure of curiosity. It is a limit built into the way physical knowledge works. Even inside our own cosmos, we already live with horizons. The observable universe is not the whole universe. It is the region whose light has had time to reach us since the early cosmic expansion began. Its radius is often given as about 46.5 billion light-years, not because the universe has a wall there, but because space has been expanding while light has been traveling. Beyond that horizon, there may be more of the same cosmic fabric, but its light has not reached us and may never reach us depending on the expansion history. This means we do not need the multiverse to learn humility. Our own universe already contains places that are real in principle, yet unavailable in practice. The boundary of observation is not the boundary of existence. It is the boundary of received information. And if that is true for distant regions of our own space, it becomes even more severe for possible multiverse scenarios. A bubble universe produced by inflation could be forever carried away by expanding space-time. A quantum branch, if that interpretation is correct, would not be separated by ordinary distance at all, but by decoherence, meaning the histories no longer interfere in a way observers can access. A universe with different physical conditions might not share the same channels through which matter, radiation, or time behave. In each case, the problem is not that we have weak tools. The problem is that the idea may describe domains with no bridge to our experiments. This is where the multiverse becomes scientifically controversial. Science is not just a collection of interesting possibilities. It is a method for sorting possibilities by evidence. A good scientific idea must connect to observation somehow, even if indirectly. If a multiverse model is part of a broader theory that makes testable predictions inside our universe, then it can be studied through those predictions. Inflation, for example, can be tested through patterns in the cosmic microwave background and the large-scale structure of the cosmos, even if other inflationary regions remain beyond direct view. A theory involving extra dimensions might be constrained through particle experiments, gravity tests, or cosmology, even if we never travel into those dimensions. But if the only thing a multiverse proposal says is other universes exist, and nothing about them can affect anything here, then the idea becomes almost impossible to prove scientifically. It may remain philosophically interesting, perhaps even logically possible, but it does not become established knowledge. This is the thin line we must walk. The multiverse might be a real consequence of a theory that earns trust in other ways, or it might be an elegant speculation that forever outruns evidence. Both possibilities must remain open. The danger is not wonder. The danger is certainty without contact. Many people want the multiverse to be true because it feels emotionally satisfying. It gives every mystery a bigger room. It makes our universe feel less lonely. It offers a way to think about fine-tuning, possible laws, quantum outcomes, and cosmic beginnings. But wanting an idea to be true does not make it science. At the same time, dismissing it too quickly can also be careless. Some of the most important discoveries in science began as indirect inferences. Neptune was predicted through the gravitational disturbance it caused before it was seen. Black holes were once mathematical possibilities before astronomy made them concrete. Gravitational waves were predicted long before they were detected. The lesson is not that every bold idea becomes true. The lesson is that invisible things can become scientific when they leave consequences. The multiverse may stay beyond us if it leaves none, or it may become partially knowable if it leaves enough fingerprints in the theories and data we can test. The cosmic microwave background has been searched for unusual patterns that might hint at early interactions or inflationary history, but no statistically decisive multiverse signal has been confirmed. Particle physics has searched for signs of extra dimensions or new physics, but no clear portal to other realities has appeared. Cosmology continues to refine what inflation may or may not have been, but the larger question remains unsettled. This does not mean the search has failed. It means the universe is teaching slowly. Sometimes science advances not by finding the thing directly, but by narrowing the space where it could hide. A negative result is still information. A missing signal still shapes the map. If other universes exist, they may be so disconnected that their silence is not accidental. It may be their defining feature, and that silence forces a difficult philosophical question. Can something be real if it can never be known? In everyday life, you might say no because reality usually touches you somehow. But cosmology stretches the meaning of reality beyond human convenience. A galaxy beyond our future horizon may exist even if no signal from it ever reaches Earth. A region outside our observable patch may be part of the same larger space-time, even if it is forever absent from our sky. The issue is not existence alone. The issue is justified belief. Science may allow us to say, our best theory suggests this, without allowing us to say, we have proven it. That difference is small in wording and enormous in honesty. The multiverse might stay forever beyond us because proof requires a conversation, and some realities may never answer. Still, the thought does not have to end in frustration. There is a kind of beauty in recognizing a true limit. A horizon gives the sky its shape. A silence can teach the mind where certainty ends. If the multiverse remains beyond us, it will not make our universe less meaningful. It will make our knowledge more humble. We will continue to study the evidence available here. The ancient light, the expansion of space, the behavior of particles, the geometry of gravity, the patterns of galaxies, the strange precision of physical law. We will ask whether these clues point to a larger reality, while remembering that a clue is not a conclusion. And perhaps that is the mature form of cosmic wonder. To stand before the possibility of other universes without turning them into a belief too quickly. To let the unknown remain large without making it dishonest. The multiverse may exist forever outside our reach, not as a secret waiting for the right key, but as a reminder that reality may be deeper than observability. And here, inside the one universe that has reached us, you are left with a quieter responsibility, to understand as much as can be understood, to doubt as carefully as you wonder, and to live inside the known without pretending it is all there is. Could two universes ever collide? If another universe ever struck ours, you might expect the sky to crack open, but the evidence, if any existed, would probably be far quieter. A faint scar in the oldest light we can observe. The phrase, two universes colliding, sounds violent in a human way, like planets smashing or galaxies tearing each other apart. Yet in modern cosmology, the idea is stranger and more delicate. It does not usually mean two completed universes drifting through ordinary space until they bump like objects in a dark room. It means that in certain models of eternal inflation, separate bubble-like regions can form within a larger, inflating background. And if those regions expand into one another early enough, their boundaries might meet. The collision would not be something happening in our sky today, like a visible explosion. It would belong to the deepest past, to the earliest architecture of our cosmic region, before stars, planets, oceans, or eyes existed. If such a meeting happened near the beginning of our bubble's history, it might have disturbed the otherwise smooth pattern of the young universe, leaving behind a subtle imprint that could, in principle, be searched for in the cosmic microwave background, the ancient afterglow from the early universe. That is the first important lesson. A universe collision, if it means anything scientifically, is not a movie scene. It is a possible early universe event whose fingerprints would be statistical, faint, and difficult to separate from ordinary cosmic variation. Imagine a still pond, not because the universe is a pond, but because the idea helps. If a disturbance passes through before the surface freezes, the frozen surface may preserve a slight unevenness long after the disturbance is gone. The cosmic microwave background is a little like that preserved surface. It is not a photograph of the Big Bang itself, but it is the oldest light released once the universe cooled enough for radiation to travel freely. It carries tiny temperature differences, small irregularities that later helped matter gather into galaxies. If our bubble universe had collided with another bubble in an inflationary scenario, some researchers have suggested it might leave a disk-like or circular pattern, a region of unusual temperature or polarization, or a broad asymmetry across the sky. But this is not proof that such a collision happened. It is a search strategy. Scientists ask, if the theory were true, what might we see? Then they compare that expectation with data from missions that have mapped the early universe. So far, there is no confirmed evidence that our universe collided with another. There have been hints, anomalies, and debated features in the cosmic microwave background, but nothing strong enough to say, this is the mark of another universe. And that caution is not weakness. It is what keeps wonder from turning into superstition. The universe is full of patterns, and human beings are very good at seeing meaning in patterns. A cold spot, a ring, a statistical oddity. These may be clues, or they may be noise, or they may point to something entirely different. The scientific task is to resist the thrilling answer until the evidence earns it. Still, the possibility is powerful because it offers one of the rare ways the multiverse might leave a trace inside our observable universe. Many multiverse ideas are difficult to test because other regions are beyond contact forever. But a collision would be different. It would be a moment when another cosmic region did not remain completely separate. It would have touched the history of ours, not as a visitor arriving late, but as a pressure applied at the beginning. The effect might be tiny from our perspective now, stretched across billions of years of expansion, weakened into a whisper in the background radiation. But if detectable, it would change the status of the multiverse from distant speculation to something with observational consequences. That is why researchers take the idea seriously while still treating it carefully. There are also deeper questions hiding inside the word collision. What happens at the boundary between two bubble universes? Do their physical conditions match, or do they differ? Would the collision create a wave of energy, a domain wall, a region where the vacuum state changes, or a disturbance that expands through one or both bubbles? The answer depends on the model. Some collisions might be mild enough to leave only a subtle signal. Others might make a region uninhabitable. Some might never enter the part of the universe we can see. And if the collision were too strong or too close, perhaps a universe like ours would never have developed calm enough conditions for galaxies and life. This means your existence already places a quiet filter on the question. If a collision happened, it could not have destroyed the basic conditions that allowed this branch of cosmic history to unfold. The fact that you are here, listening, breathing, thinking, means any such event would have had to be survivable from the perspective of our cosmic region. That is a humbling constraint. It reminds us that not every possible event becomes part of a world that can remember it. And so the idea of colliding universes becomes less about spectacle and more about traces, limits, and patience. We may never know whether another bubble touched ours. We may search the ancient light and find nothing decisive. We may improve our maps of cosmic polarization, build sharper theories, and still discover that the universe has hidden its larger story too well. But even the question teaches you something real. The early universe may not have been an isolated beginning, sealed away from everything else. Its shape, smoothness, and faint irregularities may carry messages from processes far beyond ordinary visibility. Maybe those messages are only from inflation itself. Maybe they are from unknown physics. Maybe, though no evidence yet proves it, one of them is the fossil of contact with another cosmic region. And if that is true, then the sky above you is not merely space filled with stars. It is a surface of memory, carrying the oldest wounds and quietest signatures of reality's birth. A collision between universes would not need to be loud to be important. It would only need to leave one honest mark, faint enough to challenge us, clear enough to survive doubt, waiting in the ancient light for a mind patient enough to notice. The difference between the universe and the observable universe. The word universe sounds like it should mean everything, but the observable universe means something far more personal. Everything that has had enough time to reach us. That difference is not a small technical detail. It is one of the most important distinctions in cosmology because it separates reality itself from the portion of reality that can enter our instruments, our eyes, our equations, and our history. When people hear that the observable universe has an edge, they often imagine a giant sphere with Earth near the middle, as if we are sitting inside a cosmic bubble, and beyond its surface there is either nothing or some forbidden outside. But the edge of the observable universe is not a wall in space. It is not the end of galaxies. It is not a place where a traveler would arrive and see darkness stop. It is a horizon made by light, time, and expansion. The universe is the total thing, whatever its full size and shape may be. The observable universe is only the region from which light and other signals have had time to arrive since the early universe became visible to us. This means the observable universe is not centered on Earth because Earth is special. It is centered on us because observation is always centered on the observer. If there were an astronomer on a planet billions of light years away, that observer would have their own observable universe centered on them. Some of what they could see would overlap with what we see. Some would not. They might observe regions forever hidden from us, while missing regions that are visible in our sky. The observable universe is therefore not the universe's official boundary. It is our cosmic window, and windows can be vast without being the whole house. To understand this clearly, think about how light works. Light travels fast, but not infinitely fast. When you look at the moon, you see it as it was a little more than 1 second ago. When you look at the sun, you see it as it was about 8 minutes ago. When telescopes look at distant galaxies, they see them as they were millions or billions of years in the past. So the farther we look, the further back in time we are seeing. The deepest observations are not merely looking across space. They are looking into earlier chapters of cosmic history. But there is a limit. The universe has a finite age, and light has only had a finite amount of time to travel. On top of that, space itself has expanded while the light was moving, stretching the distances between us and the places that emitted that light. This is why the observable universe is much larger than a simple calculation based only on the age of the universe might suggest. The oldest light we can observe came from matter that is now far beyond the distance it was when the light began its journey. Space expanded during the message's flight. The message arrived, but the source region moved farther away in the cosmic sense. That is why cosmologists say the observable universe reaches tens of billions of light years in every direction, even though the universe itself is about 13.8 billion years old. This is not a contradiction. It is the effect of an expanding universe, where the stage grows while the actor's signals are still crossing it. But the observable universe has another boundary that is even more subtle. We cannot see all the way back to the first instant with ordinary light. The early universe was once so hot and dense that light could not travel freely. Photons were constantly scattered by charged particles like headlights trapped in an endless fog. Only after the universe cooled enough for neutral atoms to form could light move freely across space. That released light is what we now detect as the cosmic microwave background. It is sometimes treated like the back wall of the observable universe, but it is really a surface in time. The earliest ordinary light we can directly see. Before that, the universe is not necessarily unknowable, but it cannot be observed with normal light. Scientists must infer earlier events through indirect evidence, such as patterns in that ancient radiation, the distribution of galaxies, or possible signals from other cosmic messengers. So the observable universe is limited in two ways: outward by distance and backward by transparency. It is not everything that exists. It is everything that can, in some form, report itself to us. The universe beyond that may be larger, perhaps enormously larger, perhaps infinite, but we do not know. This is where careful language matters. Saying, "The universe is 93 billion light-years across," usually refers to the observable universe's diameter, not the full universe. The full universe may be far larger. It may be infinite. It may be finite, but so large and gently curved that our observable region looks almost flat, the way a small patch of Earth looks flat beneath your feet, even though the planet is round. It may even have a global shape that loops in a way we have not detected. Cosmology can measure the visible patch with remarkable precision, but it cannot simply step outside the patch and inspect the whole. That is why the difference between the universe and the observable universe is not just about size. It is about humility. The observable universe is data. The universe is the unknown totality that data belongs to. The observable universe contains all galaxies whose light has reached us, all ancient radiation we can map, all signals that have entered our causal past. The full universe may contain regions whose signals have not arrived and may never arrive. Those regions are not imaginary simply because they are unseen. They may be as real as our region, but absent from our evidence. And science must respect that distinction. It can say what we observe. It can infer what best explains those observations. It can test models about the larger whole, but it should not pretend that the visible portion automatically equals all of existence. This distinction also protects us from a very old mistake, confusing our perspective with the center of reality. Long ago, humans placed Earth at the center because everything seemed to move around us. Later, we learned that Earth orbits the Sun. Then we learned the Sun is one star among hundreds of billions in the Milky Way. Then the Milky Way became one galaxy among countless others. The observable universe continues this lesson. We appear to be at the center of what we can observe, but only because every observer stands at the center of their own horizon. It is a center of viewpoint, not a center of importance. The universe does not point to us. The light reaching us defines a sphere around us. That is all. And yet, there is something deeply moving about that. Every image of the cosmos, every distant galaxy, every measurement of the ancient background glow is part of the universe that has managed to reach our small location. The observable universe is not small. It contains more galaxies than the mind can comfortably hold, more stars than any human lifetime could count, more history than language can easily carry, but it may still be only a fraction, perhaps a tiny fraction, of the whole. This gives the night sky a strange double meaning. It is vast enough to humble you, yet limited enough to remind you that even vastness can be local. When you look upward, you are not seeing the universe in its entirety. You are seeing the universe's reply to our position in time and space. You are seeing the messages that made it here. Beyond them may be more silence, more structure, more cosmic history continuing without ever entering our story. And perhaps that is the real lesson. The universe is what exists. The observable universe is what can be known from here. One is reality. The other is reality filtered through time, light, expansion, and location. You live inside both. Your body belongs to the universe, whatever its full extent may be. But your knowledge belongs to the observable universe, the portion that has crossed the darkness and arrived. So the difference is not merely scientific, it is almost emotional. It tells you that knowledge is precious because it is partial. It tells you that every photon reaching a telescope is a survivor of distance. It tells you that the known cosmos is not a possession, but a gift delivered across time. And beyond that gift, the full universe may continue, unseen, unmeasured, perhaps endless, not waiting for us, not hiding from us, simply existing beyond the horizon of what any one observer can ever call their own.